French fries, chicken nuggets, and twister fries are designed to come out crispy and identical every time. Inside industrial food plants, potatoes are cut at high speed, while minced chicken is flash fried in precise oil temperatures. In this video, we follow the full factory process from raw ingredients to frozen bags, revealing how seasoning and rapid freezing lock in that crunch before it ever hits the fryer. French fries begin as raw potatoes that are converted into uniform sticks through washing, peeling, cutting, surface starch control, moisture management, pre-frying, rapid freezing, and final packaging that protects texture. Potatoes arrive with variation in size, solids content, and sugar level. The first processing goal is to standardize what enters the cutting line. Bulk hoppers feed a flume that uses water flow to move potatoes gently while separating stones and heavy debris in a trap section. The stream passes over dewatering screens that remove excess water before. Inspection systems measure size and detect defects by color. Sizing matters because cutters are tuned to a specific potato diameter. An automated grater routes smaller potatoes to thinner cut lines and larger potatoes to standard cut lines. This reduces short pieces and improves yield. Potatoes that are too small or misshapen are diverted to products that do not require long sticks. Washing follows with high turbulence jets and rotating drums. The goal is to remove soil that would dull blades and stain the surface during heating. The wash stages often alternate between immersion and spray, so dirt is loosened then flushed away. A final rinse uses cleaner water to prevent redeposition of fine silt. Peeling comes next, and it is chosen based on the desired surface and yield. Steam peeling is common for high throughput lines. Potatoes enter a pressure vessel where steam heats the skin rapidly. The pressure is released in a fast vent, which causes the skin to separate from the flesh. Rubber disc peelers then rub off loosened skin while minimizing flesh loss. Abrasive peeling can be used when steam conditions are not optimal. Abrasive peelers use rotating carborundum surfaces that physically grind away the peel. After peeling, the potatoes are trimmed. Optical sorters detect remaining skin patches and dark defects. Air jets or mechanical diverters remove defective potatoes from the main stream. Manual style trimming is not the focus here. The key is that defect removal happens before cutting, so defects do not spread into many pieces. The peeled potatoes move into a water-filled surge channel. This surge stabilizes feed rate into the cutters. Consistent feed prevents blade shatter and size variation. The water also reduces surface browning before the next steps. Cutting converts whole potatoes into sticks with a defined cross-section. A water knife cutter is typical for straight fries. Potatoes are aligned and pushed through a grid of sharp blades. The grid spacing defines fry thickness. The cut sticks exit into flowing water that carries them away from the blades. This water stream prevents pieces from sticking together, and it flushes surface starch immediately. Blade condition is a major driver of shape. Sharp blades create clean edges and reduce feathering. Dull blades tear cell walls and create ragged surfaces. Ragged surfaces absorb more oil and shed more fragments later. Cutter systems monitor pressure and vibration to indicate blade wear. Blades are replaced or sharpened on a schedule, so cut quality stays stable. After cutting, the stream is a mix of sticks and small fragments. Screens separate fines and short pieces. The target product stream continues forward. The fine stream can be routed to other products or rework systems. Removing fines early prevents them from burning during frying and prevents dark specks in the final pack. The next objective is surface starch control. Freshly cut potatoes release starch that forms a sticky film. If that film remains, it causes clumping and uneven frying. Sticks enter a series of wash flumes with controlled agitation. The water flow is tuned to remove loose starch without breaking edges. Countercurrent washing can be used so the cleanest water contacts the cleanest sticks near the exit. After washing, the sticks are dewatered. Vibratory shakers and air knives remove surface water. Excess water would cool blanches and fryers. It would also cause oil spatter during frying. Dewatering improves energy efficiency and improves texture control. Blanching is the next major transformation. Sticks enter a hot water blancher, where temperature and time are controlled tightly. Blanching partially gelatinizes surface starch and sets the outer layer. It also leaches out some sugars and adjusts color development potential. This step is critical for preventing excessive browning during frying. Blanching also softens the interior, so final cooking yields a fluffy center. Blanching conditions are chosen based on potato chemistry. Potatoes with higher reducing sugars brown faster in oil. For those lots, blanching can be longer or warmer to pull more sugars out. For low sugar, lots blanching can be lighter to preserve flavor and yield. Inline color prediction models can adjust blancher set points when raw material shifts. Some lines include a second blanch or a dip treatment. A dip can include dextrose for controlled browning when potatoes are too pale. A dip can include sodium acid pyrophosphate to limit grey discoloration and stabilize color. These additions are process tools that tune appearance. They are applied in controlled concentration and then drained. After blanching, the sticks are cooled or rinsed briefly. Cooling stops cooking and removes surface solubles. Rinsing also removes residual dip solution when used. The sticks are then dewatered again because the next step relies on controlled moisture. Drying is often used before frying. Drying reduces surface moisture, so the fries form a crust faster in oil. Drying also reduces oil breakdown because less water enters the fryer. Dryers use hot air moving across a vibrating bed or a conveyor. Air temperature and velocity are tuned so the surface dries without hardening the interior. The target is a specific weight loss that correlates with final crispness. Now the product enters pre-frying. Pre-frying is a short, high-temperature oil cook that forms the initial crust and sets the structure. The sticks pass through a continuous fryer on a mesh belt. Oil temperature is maintained within tight limits. Residence time is controlled by belt speed and by product bed depth. Too long a fry makes the crust too thick and the interior too dry. Too short a fry yields weak structure that collapses during freezing. During pre-frying, water flashes from the surface and creates a porous crust. Steam pressure moves outward and leaves behind channels. These channels later contribute to crispness after final cooking. Oil enters the crust as water leaves. The balance between moisture loss and oil uptake is controlled by temperature and time. A well-tuned pre-fry produces a crust that is strong but not greasy. Oil management is part of process stability because degraded oil changes heat, transfer, and flavor. Filtration systems remove crumbs that would burn and darken the oil. Fresh oil is added to maintain quality and correct polar compounds. Fryers use circulation to keep temperature uniform across the belt width. Uniform temperature prevents striping where one side browns more. After pre-frying, the fries are de-oiled. Shakers remove excess surface oil. Air blowers can strip oil film from the surface. Removing surface oil improves packaging and reduces clumping during freezing. It also improves final texture because excess oil can soften the crust. At this point, seasoning can be applied for certain products. Fine salt or specialty powders are dosed in a tumbler while fries are still warm. Warm surfaces help adhesion. The seasoning rate is controlled by mass flow feedback. Even distribution is achieved by gentle tumbling that avoids breaking edges. The next critical step is freezing. Freezing preserves structure and prevents fries from sticking in the bag. Industrial lines use individual quick freezing. Fries enter a freezer tunnel where very cold air flows at high velocity. The fries are carried on a belt or fluidized on a perforated deck. Fluidization lifts and separates pieces so they freeze individually. Rapid freezing forms small ice crystals and reduces cell damage. Reduced cell damage helps the interior stay fluffy after final cooking. Chicken nuggets are manufactured by converting deboned poultry meat into a uniform seasoned matrix, forming that matrix into consistent shapes, applying a multi-layer coating, setting the coating with a brief fry, then freezing and packaging so each nugget cooks evenly later. Production starts with raw meat, preparation and temperature control because texture depends on protein functionality. Chilled poultry meat arrives as trimmed pieces that are routed into grinding lines. The first mechanical step reduces size, so mixing becomes predictable. Meat passes through a coarse grinder plate that creates uniform chunks rather than smear. Coarse grinding also exposes protein surfaces that will later bind water and fat. After coarse grinding, the meat enters a blending stage where different raw streams are combined to hit target composition. Lean meat and higher fat portions are balanced to reach a specified fat level. This balance affects juiciness and bite. If the formulation uses skin or added fat, it is incorporated as a controlled stream. The blend is kept cold because warm meat smears and prevents clean particle definition. The blended meat moves into a fine grinding or emulsification step depending on the target nugget style. For a formed nugget with a smooth interior, the line uses an emulsifier or bowl chopper. Rotating knives cut the meat while mixing paddles fold it. Salt is added early because it solubilizes myofibrillar proteins. Those proteins create the binding network that holds the nugget together after cooking. Water or ice is added in a measured dose to manage temperature and to hydrate proteins. Ice is often preferred because it cools while adding water. If a coarser bite is desired, the line uses a smaller plate grinder rather than full emulsification. This preserves visible meat texture. Some formulations combine both approaches. A portion is emulsified to act as binder, and a portion remains coarser for texture. The two streams are then recombined in a mixer. Seasoning and functional ingredients are added in the main mixing system. Spices and flavors are introduced as dry blends or as slurries for better distribution. Phosphates may be used to increase water binding and improve yield. Starches or proteins can be included to stabilize the matrix and reduce purge. Each ingredient is metered by weight to maintain consistent salt level and viscosity. Mixing is done in a vacuum mixer in many high-volume lines. Vacuum removes trapped air that would create holes and weak spots. The mixer uses paddles that knead rather whip whip. Kneading develops a cohesive paste without overworking. Overworking can make the final bite rubbery. The end point is judged by paste appearance and by torque and by temperature. Once the meat batter reaches specification, it is transferred to forming. Forming turns the paste into nuggets with uniform mass and shape. A common method uses a forming drum with shaped cavities. The paste is pumped into the drum under pressure. Cavities fill, and then a stripper plate releases formed pieces onto a conveyor. A second method uses a die and cutter system that extrudes a sheet and stamps shapes. Both methods aim for tight weight control because cooking and packaging rely on consistent mass. Forming pressure and paste, viscosity are adjusted together. If viscosity is too low, the pieces slump and lose definition. If viscosity is too high, cavities do not fill and voids appear. Temperature is again a key variable. Colder paste holds shape better but becomes harder to pump. Warmer paste pumps easily but can smear and soften. The line holds a narrow temperature window that supports both pumping and definition. Formed pieces move immediately into a coating system. Coating is usually multi-layer because it needs both adhesion and texture. The first layer is pre-dust. Pre-dust is a dry flour or starch blend that coats the wet surface and creates a dry interface. This layer improves batter pickup and reduces bare spots. Pre-dust is applied in a curtain or a tumbler where pieces roll through powder. Excess pre-dust is shaken off so the layer remains thin. After pre-dust, the nuggets enter batter. Batter is a liquid suspension that contains flour and starch and leavening and seasonings. The batter tank uses agitation to keep solids suspended. Viscosity is controlled by water ratio and by temperature. Too thin a batter yields weak coverage. Too thick a batter creates heavy ridges and poor bite. Batter is applied by submersion or by waterfall curtain. Submersion ensures complete coverage. A blow-off or air knife can remove excess batter and set a uniform thickness. Next comes the outer breading. Breading can be fine crumbs for a smooth surface or coarse crumbs for a crunchy profile. Pieces pass through a bed of crumbs while top conveyors press crumbs into the batter. This is called a compression pass and it improves adhesion. Breading pickup is monitored because it affects final weight and texture. Crumb flow is maintained by vibration and recirculation. Broken crumbs and fines are screened out because they create dusty surfaces. Some nugget lines use a double batter and breading system. In that case, the pieces receive a first batter and a first crumb, then a second batter, then a final crumb. This builds a thicker crust that stays crisp longer. Each stage must be controlled so the coating does not become too heavy. Excessive coating can crack during frying and create blowouts. After coating, the surface must be set so it does not fall off during handling. Setting is done with a short fry. The nuggets enter a continuous fryer where hot oil rapidly gels the batter and fixes the crumb. This fry is not intended to fully cook the interior in many processes. It is designed to create a stable crust and to develop initial color. Fry temperature and residence time are tuned to coating style. A fine crumb coating sets quickly. A coarse crumb needs enough time for oil to penetrate and bind contact points. If the fry is too short, crumbs shed in later conveyors. If the fry is too long, the crust becomes too dark and oil uptake increases. Oil circulation keeps temperature uniform and prevents cold spots at the product entry. During frying, the coating undergoes several transformations. Water flashes as steam and creates pores in the crust. Starches gelatinize and then begin to dry into a rigid network. Proteins in the batter coagulate and lock the structure. The crumb absorbs a small amount of oil that later contributes to crispness. The surface color begins to form through browning reactions. After frying, excess oil is removed. The nuggets pass over vibrating de-oiling conveyors. Air blowers strip surface oil from crevices. Removing surface oil reduces clumping during freezing. It also reduces fat variability across pieces. The goal is a stable, predictable oil pickup level. Depending on product design, the nuggets may then pass through an oven step. An oven can set the interior further without adding more oil. It can also reach a target lethality endpoint before freezing. Ovens use hot air impingement to heat quickly. Heat transfer is controlled so the coating does not overbrown. This step is used when the product must be fully cooked before packaging. Whether cooked by fryer alone or by fryer plus oven, the nuggets are then cooled briefly before freezing. Cooling reduces surface heat load on the freezer. It also reduces moisture condensation. Cooling is done with high airflow at controlled temperature. The nuggets then enter an individual quick freezer. In the freezer, cold air freezes the nuggets rapidly. Rapid freezing preserves juiciness by forming smaller ice crystals. It also locks the coating structure, so crumbs do not soften and fuse. Nuggets travel on a belt through zones of progressively colder air. In some designs, the nuggets are lightly fluidized so they do not stick together. The exit temperature is driven low enough that the core is fully frozen. After freezing, the product is screened and sorted. Screens remove frozen fines and loose crumb. Optical systems can remove misshapen pieces or twins that stuck together before freezing. Metal detection and X-ray inspection can occur after freezing because product flow is stable and consistent. Frozen nuggets then move to weighing and packaging. Multi-head weighers portion exact weights. Chutes are designed to reduce impact because frozen nuggets can chip. Bags are formed and sealed quickly to limit moisture exposure. The packaging film must provide a strong moisture barrier. Moisture barrier prevents freezer burn, which dries the crust and toughens the interior. Sealing is tuned so crumbs do not contaminate the seal area. Fill timing allows product to settle before seal jaws close. Bags are cut and then conveyed to case packing. Cases are packed to prevent excessive compression that could crush coating. Finished cases go to frozen storage, where temperature stability preserves texture. The main technical controls for chicken nuggets are protein extraction during mixing and coating adhesion during breading and set during frying. Protein extraction is controlled by salt level and mixing energy and temperature. This defines how well the nugget holds together. Coating adhesion is controlled by pre-dust coverage and batter viscosity and crumb size. Set is controlled by fry temperature and time. Freezing then protects both the interior network and the crust porosity. Uniformity depends on tight control of piece mass and coating pickup. Piece mass sets thermal behavior during final cooking. Coating pickup sets crust thickness and browning rate. If mass varies, the consumer cook produces mixed doneness. If coating pickup varies, the bag contains some pieces that brown too fast and some too slow. The line therefore continuously monitors weights and adjusts forming pressure and batter viscosity and crumb feed. Twister fries begin at the cutting head because the entire process is built around preserving a continuous spiral that would otherwise snap under its own weight. Potatoes are first selected for geometry and solids. Long oval potatoes are favored because they can produce a longer helix with fewer breaks. High dry matter is targeted because the spiral shape exposes more surface area and therefore loses moisture faster in later steps. Reducing sugar level is controlled because a spiral browns faster than a straight stick at the same fry conditions. The potatoes arrive in bulk and flow into a water flume that moves them while separating heavy debris. A stone trap section uses low velocity zones so stones settle out. The stream then passes through spray washers that strip soil from eyes and creases. A rinse stage follows so fine grit does not travel into peelers and cutters. Dewatering screens lift the potatoes out and present them to the next stage with minimal carryover water. Sizing and grading follow because a spiral cutter must match the potato diameter. Optical systems measure length and diameter and reject misshapen pieces. Size grading also improves cut stability because the cutter settings can stay constant for a given lane. Potatoes that are too small create spirals that are fragile and short. Potatoes that are too large overload the cutting head and increase fracture. Peeling prepares a clean surface so the spiral ribbon has consistent strength. Steam peeling is common for this product because it minimizes flesh loss and keeps the surface smooth. Potatoes enter a pressure vessel where steam heats the skin rapidly. A rapid pressure drop separates the skin from the flesh. Rubber disc peelers then remove loosened peel without digging into the potato. A brief trim step removes remaining peel patches because peel can act as a tear line in the spiral. After peeling, the potatoes move through a chilled buffer flume that stabilizes feed. Consistent feed rate prevents cutter surges. The buffer also keeps exposed potato surfaces wet to limit browning before cutting. The potatoes are then aligned and fed into the spiral cutting system. Spiral cutting uses a rotating blade and a centering mechanism that drives the potato forward while turning it. The potato is skewered or held between opposing grips so it rotates around a defined axis. A continuous blade slices into the surface and advances along the potato length at a fixed pitch. Pitch is the axial distance per rotation, and it defines the tightness of the spiral. A tighter pitch yields more turns and a denser appearance. A looser pitch yields wider gaps and a more open helix. Many twister formats also use a cross-section cutter combined with the spiral motion. As the potato advances, the system forms a ribbon with a defined thickness and width. Thickness control is critical because thin ribbons break during handling. Thick ribbons lose crispness and cook unevenly. The cutter therefore uses rigid guides and sharp blades to create a consistent ribbon thickness. As the spiral ribbon exits the cutting head, it is fragile and saturated with surface starch. It is immediately supported by water flow or a soft belt, so it does not stretch. Water transport serves two purposes. It supports the helix mechanically, and it begins washing away loose starch. Loose starch creates stickiness that can cause coils to fuse. The spiral stream passes through a separation section that removes end pieces and fragments. Broken spirals become shorter curls and fines. These are screened out because they fry too fast and darken. The main product spirals continue into a gentle wash system. The wash is tuned to reduce surface starch without tearing the ribbon edges. Countercurrent flow can be used so the cleanest water contacts the cleanest spirals at the exit. Dewatering follows, and it is more delicate than for straight fries. A standard shaker can snap spirals if vibration amplitude is high. Twister lines therefore use low amplitude, vibrating, dewatering, or belt drainage with air knives. The aim is to remove free water while keeping the helix intact and separated. Blanching is the next structural step, and it does more than control color. Blanching partially gelatinizes starch at the ribbon surface and slightly softens the interior so the spiral can flex without cracking. The spirals enter a hot water blancher on a mesh belt. Belt speed sets residence time, and water temperature sets the degree of gelatinization. Blanching also leaches out some reducing sugars to moderate browning later. Because spirals have high surface area, blanching is tuned carefully. Over-blanching makes the ribbon too soft, and it can stretch and deform. Under blanching leaves the surface raw and fragile and increases breakage during frying. The target is a ribbon that has enough set to keep its edges smooth, yet enough flexibility to survive conveyors. If the product is designed for a specific golden color, a dip stage may follow blanching. A light dextrose dip can be used when potatoes are too pale. A color stabilizing dip can be used to reduce gray discoloration. The dip is applied in a controlled tank and then drained. The spirals then pass through a rinse or a brief spray, depending on the recipe strategy. After blanching and optional dips, the spirals are dewatered again. This stage has strong impact on oil uptake. Excess surface water delays crust formation and increases oil absorption. Dewatering is done with a combination of drainage and air. Air velocity is tuned so it strips water without whipping spirals into tangles. Conveyors are designed with minimal drops because drops twist spirals into knots. Pre-drying may be used before frying. Drying removes surface moisture and helps set the helix. It also helps maintain separation because drier surfaces are less tacky. Drying is done with warm air across a belt. Temperature is kept moderate so the spirals do not cook. The target is a controlled weight loss that correlates with later crispness. Now, the spirals enter par frying. Par frying sets the outer crust and locks the spiral geometry. The spirals pass through a continuous fryer on a belt that keeps them submerged and separated. Oil temperature is controlled tightly because spiral. Surface area causes rapid heat transfer. Residence time is set so the crust forms, but the interior remains partially cooked. This supports later final cooking while keeping factory oil uptake in a controlled band. During par frying, water flashes from the surface and creates a porous crust. The porous crust is essential for final crispness. The spiral shape creates many edges, and those edges brown faster. The fryer therefore uses uniform oil flow to avoid hot spots. Oil circulation and baffles keep temperature even across the fryer width. The bed depth is controlled because deep beds reduce oil contact and create uneven color. Oil uptake is influenced strongly by cooling dynamics. As spirals leave the fryer, internal steam pressure drops and oil can be drawn into pores. To limit this, the line removes surface oil quickly. Vibratory conveyors shake off excess oil. Air blowers strip oil from folds and inner turns. This reduces greasy spots and reduces clumping during freezing. Burger King hamburgers begin at industrial scale meat processing facilities, where fresh beef trimmings are delivered in vacuum-sealed containers maintained below 4 degrees Celsius. The trimmings are offloaded into chilled receiving areas equipped with stainless steel conveyors and holding bins. The bins feed directly into grinders fitted with cutting plates calibrated to a precise perforation diameter between 3.2 and 4.8 millimeters. The grinding process is conducted under controlled temperatures to prevent protein denaturation and inhibit microbial growth. The ground beef is transported via enclosed auger systems into horizontal ribbon blenders that homogenize the mixture to a target lean-to-fat ratio of approximately 80-20. Blending continues for 90 to 120 seconds at low RPM to avoid heat buildup. Each batch is sampled for moisture content, fat dispersion, and microbial contamination. No seasonings, fillers, preservatives, or additives are introduced. Quality-approved batches are routed directly to the forming line. The forming process uses hydraulic form and eject systems with rotary dies that compress the meat into circular patties of fixed mass, diameter, and thickness. Optical sensors monitor patty integrity, checking for cracks, underfilled molds, or edge defects. Formed patties are placed onto poly-coated food-grade conveyor belts and immediately pass through a metal detection tunnel calibrated to detect ferrous and non-ferrous contaminants as small as 1.0 millimeter. Patties then enter a spiral freezer where air chilled to 35 degrees Celsius circulates at high velocity to harden the product within 7 to 10 minutes. Rapid freezing limits ice crystal growth and preserves cell structure. Upon exit, frozen patties are automatically stacked in counted layers into polyethylene-lined cartons. Each carton is sealed, labeled with a unique batch code, production timestamp, and storage requirements, then palletized and transferred to cold storage held at 20 degrees Celsius or lower. Frozen patties are shipped in refrigerated trailers equipped with continuous temperature logging devices that provide data on transit conditions. At Burger King distribution centers, incoming pallets are scanned into inventory and stored in walk-in freezers. Orders are fulfilled based on store demand algorithms, with frozen patties delivered to individual restaurants on a rotational inventory system that ensures first in, first out usage. At the restaurant level, frozen patties are stored in low temperature freezers until transferred to refrigerated drawers for same-day cooking. Each drawer maintains internal temperatures between 1 and 4 degrees Celsius. Restaurant operations follow a grill-to-order or batch preparation method depending on volume. Cooking is done using a proprietary gas-fired broiler system equipped with a continuous stainless steel chain conveyor that transports raw patties through a tunnel with overhead and under-fired direct flame burners. Each patty is manually placed onto the moving broiler belt, which advances at a fixed speed preset according to patty thickness and desired internal temperature. As the patty enters the broiler tunnel, infrared sensors verify burner ignition and temperature stability. The open flame directly contacts the surface of the patty, inducing a Maillard reaction that produces characteristic grill marks and seared flavor. Simultaneously, moisture is driven out of the meat surface, concentrating the flavor and forming a firm exterior crust. The broiler conveyor moves at a calibrated pace, typically between 2.5 to 3.5 minutes per pass, depending on the product type. Internal temperatures of patties are monitored via embedded thermocouples in test units during hourly quality assurance checks. Each patty must achieve an internal temperature of at least 71 degrees Celsius before being passed to the holding area. The broiler is equipped with grease drainage systems that collect rendered fat into heat-resistant trays, which are emptied and cleaned daily. Cooked patties are deposited onto a stainless steel chute that guides them into heated holding trays. These trays are equipped with radiant heat elements that maintain surface temperatures between 60 and 65 degrees Celsius. A digital timer tracks how long each tray has been loaded. Cooked patties are held for a maximum of 10 minutes before being discarded to maintain texture and taste consistency. Each tray is labeled with a batch code and timestamp for traceability. While patties are cooking, buns are processed through a vertical bun toaster equipped with conveyor-style platen heaters. Buns are stored at room temperature in sealed bags until loaded into the toaster's gravity-fed chute. Each bun is sliced horizontally, and the interior face is pressed against a heated platen set to 288-293 degrees Celsius for 9 to 11 seconds, producing a lightly toasted surface that provides moisture resistance and structural stability during sandwich assembly. At the assembly station, buns are transferred to stainless steel prep surfaces. Condiments are applied using calibrated squeeze bottles or piston-driven dispensers. Mayonnaise, ketchup, and mustard volumes are controlled to within 0.2 gram tolerance per sandwich. Pre-chopped lettuce is stored in refrigerated bins held at 1 to 4 degrees Celsius and portioned with measured scoops. Sliced tomatoes are machine-cut off-site to uniform thickness and stored in cold bins. Pickles are pre-sliced, stored in brine, and dispensed manually or by volume-controlled tongs. Onion slices are separated into rings and stored dry in chilled compartments. Cheese slices, individually separated by interleaving sheets, are held in humidity-controlled drawers and applied manually to hot patties. Melting begins on contact due to retained surface heat from the broiler. In multi-patty configurations, cheese is placed between layers to bind them together. Burger crowns are pressed gently onto the sandwich to complete assembly. Each finished burger is placed into a pre-folded paper wrap or cardboard clamshell, depending on store packaging configuration. Clamshells are pre-loaded into gravity-fed dispensers and labeled with SKU identifiers. Assembly staff insert each item into its respective packaging within 10 seconds of completion to reduce heat loss. Packaged burgers are queued on heat-retaining stainless steel chutes until collected by frontline staff or drive-through personnel. All steps of production, from raw patty to finished burger, are logged via point-of-sale integrated kitchen management systems. These systems track timestamps for cook cycles, holding durations, and ingredient usage. Broiler temperatures, toaster settings, and holding bin temperatures are verified hourly against digital readouts and documented in quality assurance logs. Ingredient rotation follows a strict first in, first out schedule. Bins for lettuce, tomato, and onions are marked with timestamps. Condiment cartridges are replaced every 4 hours. Cheese drawers are sanitized every 4 hours or upon visible residue. Packaging materials are stored in dry areas above floor level and inspected daily for contamination or damage. Cleaning procedures for the broiler include nightly shutdown and disassembly of the chain, flame shields, and drip trays. Components are soaked in degreasing solution, brushed with food-safe abrasives, rinsed with potable water, and reassembled before morning operations. Bun toasters are wiped down between shifts and deep cleaned daily. Stainless steel prep surfaces are sanitized using quaternary ammonium-based solutions between each menu changeover. Waste patties beyond holding limits are recorded and disposed of according to local food safety regulations. Waste logs categorized by reason: overcooked, expired holding time, or off-spec grill temperature. Daily waste volumes are analyzed against hourly demand forecasts to optimize future batch sizes and reduce discard rates. Every element of the system is engineered for reproducibility. Conveyor speed, burner placement, heating element calibration, and ingredient flow are all configured to produce identical results across every store. Burger King's operational procedures specify not only the quantity of each topping, but the order of application, spacing, and placement centering to reduce variability. Thermal cameras and real-time temperature logging are used in some test markets to improve process control. Wendy's hamburgers begin with the processing of fresh, never frozen beef. Whole muscle cuts are delivered to regional patty processing facilities in refrigerated containers held between 0 and 4 degrees Celsius. These cuts are trimmed of excess fat and connective tissue by mechanical blade systems equipped with thickness sensors and cutting guides to standardize input material. The trimmed beef is passed through fine grinding plates with perforation diameters ranging from 3.5 to 5.0 millimeters to produce uniform ground meat. The ground beef is loaded into stainless steel mixing tanks where the lean to fat ratio is balanced to approximately 80.20 using real-time fat analysis sensors and automated auger feeding systems. No preservatives, fillers, or additives are introduced. The blend is mixed gently under chilled conditions to prevent protein degradation and to retain water binding capacity. The mixture is tested for microbial content, temperature, and compositional accuracy before advancing. Patties are formed using hydraulic forming machines with square dies, giving Wendy's burgers their distinctive shape. Each mold is calibrated for precise weight and thickness, typically 113 to 170 grams, depending on the product line. Formed patties are transferred to a conveyor where machine vision systems inspect for edge defects, cracks, or inconsistencies in surface texture. Acceptable patties are placed into single-layer, vacuum-sealed packaging and labeled with production time, lot number, and expiration date. Packaged patties are transported to restaurant locations via refrigerated trucks maintained below 4 degrees Celsius. Upon arrival, the patties are stored in walk-in refrigerators with air circulation systems designed to maintain uniform temperatures and humidity. The storage area uses FIFO inventory rotation, tracked by internal labeling systems that log delivery and use dates. Patties are removed from cold storage and transferred to a flat-top grill for cooking. The grill is made of polished steel and heated by independently controlled heating zones, maintained at temperatures between 218 and 246 degrees Celsius. Cooking surfaces are checked for temperature consistency using surface thermometers before each service period. No oil is added to the grill surface, as the beef renders its own fat during cooking. Raw patties are placed directly on the hot surface and pressed with a weighted spatula to ensure even contact and browning. The searing process forms a crust that locks in juices and enhances flavor through Maillard reaction. Internal patty temperature is monitored using digital thermometers to ensure a minimum internal temperature of 71 degrees Celsius is reached. Cooking time ranges from 3 to 4.5 minutes per side, depending on patty thickness and grill load. Patties are flipped once during cooking using flat-edge spatulas to maintain structural integrity. Drippings are channeled into built-in grease traps that are emptied and cleaned daily. Finished patties are transferred directly to a heated holding tray set to maintain product between 60 and 65 degrees Celsius. Holding time is limited to 5 minutes to ensure texture and flavor integrity. Burger buns are delivered from certified commercial bakeries, stored in ambient conditions in dry storage areas, and used within labeled shelf life. Buns are sliced in-store using serrated rotary cutters attached to prep tables. Each half is toasted on a separate bun toaster fitted with heated platens that reach 285 to 295 degrees Celsius. Toasting duration is controlled to within 0.5 seconds per bun half to ensure uniform color and surface dryness. Toasted buns are transferred to the sandwich assembly station, where standard build sequences are followed. The sandwich station includes dedicated zones for condiments, vegetables, cheese, and protein. Mayonnaise and ketchup are dispensed using piston-based systems with adjustable volume control set to deliver consistent amounts per sandwich. Mustard and other optional sauces are applied manually in measured dollops using portion-controlled utensils. Fresh lettuce is shipped pre-cut and triple washed, stored in refrigerated prep tables between 1 and 4 degrees Celsius. Tomatoes are sliced daily using mechanical slicers to a thickness of 5 millimeters and stored in high humidity containers. Onions are peeled and sliced into rings and portioned by visual estimation or scale weight. Pickles are brined and pre-sliced, dispensed using tongs from refrigerated compartments. Cheese is individually sliced and stored in covered trays within the sandwich station's cold section. A single slice is placed directly onto the hot patty immediately after cooking. The heat from the patty softens the cheese, but does not fully melt it, preserving slice definition. Bacon, if added, is cooked separately on a flat-top griddle and held in warming drawers lined with absorbent paper and heated via low-voltage infrared elements. Assembly order follows strict guidelines. The bottom bun receives sauces and condiments, followed by lettuce, tomato, and onion. The patty is placed on top of vegetables to reduce heat transfer to the bun. Cheese, bacon, and pickles are layered above or below the patty based on product specifications. The crown bun is pressed on top to complete the build. Assembled burgers are wrapped in branded foil wrappers or placed in paperboard containers depending on order type. Wrappers are designed with heat-retaining layers and moisture vents. Burgers are staged in a holding chute or placed directly into order bags. All packaging materials are stored in dry stock rooms and replenished daily. Package weight and sandwich construction are audited periodically for consistency. Restaurant kitchens use an operations management system that logs grill usage, cooking cycles, and holding times. Thermocouple sensors embedded in the grill surface provide live temperature feedback. Digital timers alert staff when patties must be removed or discarded. Each station is monitored for compliance with production procedures via internal checks and periodic inspections. Cleaning schedules are programmed to occur at shift changes and closing. Flat-top grills are scraped after each use and cleaned with food-safe degreaser at the end of each day. Grease traps are emptied, wiped, and sanitized using quaternary ammonium-based disinfectants. Prep surfaces are wiped with single-use sanitizer wipes and tested with ATP swabs for surface cleanliness verification. Unused raw patties at the end of the day are discarded if past time limits. Opened, condiments are sealed and stored in designated cold storage with labeled expiration dates. Open vegetable containers are covered with plastic film and labeled with the date and time of preparation. All leftovers are monitored for spoilage indicators and disposed of if they exceed quality thresholds. Each restaurant uses a real-time inventory and supply tracking system linked to a central database. Usage rates for beef, buns, vegetables, cheese, and condiments are analyzed against sales data. Discrepancies trigger alerts to management and may result in retraining or procedural audits. Ingredient reorders are generated automatically based on projected demand using historical sales averages. Allergen control measures are implemented in burger production through equipment segregation and cleaning protocols. Separate spatulas and prep zones are designated for allergen-free products. Staff receive allergen training and use visual cue systems to avoid cross-contact. Labels indicate allergen presence per local regulatory requirements. Throughout the process, every input is controlled and verified to produce uniform hamburgers across locations. Cooking parameters, ingredient measurements, and build sequences are optimized for speed, consistency, and quality. Final products are subject to visual inspection, temperature checks, and build verification by designated shift managers. Any deviations are logged and addressed through corrective procedures. KFC's fried chicken may be iconic for its secret blend of 11 herbs and spices, but the factory process behind every crispy, golden piece is built on something far less mysterious: precise engineering, timed workflow, and ruthless consistency. Behind every bucket of original recipe is a production line designed to turn raw chicken into seasoned, breaded, and pressure-fried perfection on a massive global scale. Millions of pieces per day across thousands of locations, all starting in high-throughput poultry processing facilities. The process begins at the poultry plant, long before any chicken sees a fryer. KFC doesn't raise its own chickens. Instead, it partners with large-scale poultry suppliers who specialize in high-efficiency, vertically integrated operations. These facilities process thousands of birds per hour using lines that are fully automated and regulated to deliver uniform size, weight, and quality. Once chickens arrive at the facility, they're stunned and humanely slaughtered, then passed through defeathering machines. The birds are washed, eviscerated, and chilled in cold water or air-chilling tunnels, depending on the region and regulatory requirements. From here, they move to automated cutting lines, where high-speed blades segment each bird into standardized cuts: drumsticks, thighs, wings, and breasts, with specific sizing tolerances so each piece will cook evenly during pressure frying. Every piece is trimmed and inspected, then sent through water jet portioning systems, lasers, and nozzles that precisely cut meat based on optical sizing. Pieces are sorted by weight to ensure uniform cook times, then chilled to below 40 degrees Fahrenheit and packed in vacuum-sealed bags. These raw chicken portions are shipped to regional KFC prep centers or directly to KFC kitchens, depending on location. At centralized KFC prep facilities, often located near urban hubs or distribution centers, the real transformation begins. Here, each piece of raw chicken is thawed, if frozen, washed, and carefully inspected again. Workers wear full food-safe suits, gloves, and hairnets, operating under strict HACCP protocols to avoid cross-contamination. Every batch is handled in cold prep rooms, where the air is chilled and filtered to keep bacterial growth to a minimum. Then comes the marination phase, a foundational step in the flavor and texture of KFC's chicken. Each piece is soaked in a liquid brine, typically a mix of water, salt, phosphate, and other flavor-carrying compounds. The phosphate acts as a moisture-retaining agent, helping the chicken stay juicy through frying. This brine is vacuum tumbled into the meat using large rotating drums, which massage the liquid deep into the muscle fibers over the course of 30 to 60 minutes. Every load is weighed before and after to ensure absorption is within spec. Next comes seasoning. Contrary to myth, the famous 11 herbs and spices are not mixed at every location. Instead, the spice blend is produced at a secure, centralized facility where the exact combination is pre-measured and packed into coated, tamper-proof bags. These bags are shipped to prep centers or stores where they're added directly to flour for the breading process. Only a few people in the company know the full recipe, and the factory itself is designed to prevent accidental or deliberate disclosure. Even the workers handling the blend often don't know what's in it. In the prep facility, seasoned breading stations are set up in long rows where chicken moves through the legendary hand breading process. Each piece is dredged in seasoned flour, then placed in a shallow basket where it's pressed into the flour with a very specific folding and compression motion. This step, called the 7-10-7 method, is taught to every KFC cook and replicated in prep facilities worldwide. It's part of what gives KFC chicken its craggy, crunchy, uneven texture. The breaded pieces are then loaded onto trays and either flash chilled for shipment or sent directly to in-house kitchens for frying. In some markets, partially cooked chicken is sent to stores to shorten fry times during service rushes. But in most regions, frying is done fresh in-store, using the same tightly controlled procedure. In KFC restaurants, pressure fryers are the beating heart of the operation. These aren't just deep fryers, they're sealed, industrial pressure cookers that fry chicken under high pressure and temperature. The typical fryer operates at around 350 degrees Fahrenheit under 12 psi, allowing the chicken to cook faster and retain more moisture than open frying. The result? A crisp exterior with a tender, juicy interior, cooked in about 10 minutes per batch. Each piece is loaded into a wire basket or chicken clamshell, arranged in a way that ensures even oil flow. The basket is locked into the fryer, the lid is sealed, and the cook cycle begins. Once complete, the fryer releases pressure and the basket is lifted. Every batch is placed on a draining rack, where oil drips off and the crust sets. From there, chicken is either held in warming cabinets kept at a specific humidity and temperature, or served immediately, depending on demand. Quality checks are frequent. Staff use thermometers to confirm internal temperatures, visual checks to verify color and breading coverage, and taste tests to ensure consistency. Any batch that sits too long is discarded to maintain quality standards. Back in the prep centers, not all chicken ends up as original recipe. KFC also produces extra crispy, spicy, and grilled varieties, each requiring slightly different breading and cooking profiles. Extra crispy chicken, for instance, goes through a double breading process with a coarser flour blend and is fried in open fryers, not pressure ones. The breading station must be cleaned and reset between batches to avoid cross-contamination between flavors. Meanwhile, grilled chicken is seasoned differently, rubbed with a dry spice mix and roasted in combi ovens, not fried at all. These ovens use steam and convection to cook the meat evenly while keeping it juicy. The flavor is more subdued, but the factory process behind it is just as strict, with marination and seasoning steps done under cold room conditions before transport. Throughout the entire system, data is king. Every batch of chicken, from farm to fryer, is logged with timestamps, location codes, and supplier data. Digital systems track everything from fryer oil turnover rates to breading mix usage, ensuring that no store deviates from standard operating procedures. Even the oil itself is filtered between batches and replaced on a tightly controlled schedule. Sensors monitor fryers for temperature drift and alert staff if anything strays outside of spec. Sanitation is constant. Between batches, breading stations are cleaned, gloves are changed, and utensils are sanitized. The entire prep room in a factory is stripped down at the end of each shift and pressure washed with food-grade disinfectants. Air in the facility is filtered and recirculated to control temperature and humidity. Workers follow strict entry protocols, passing through air curtains and sanitizing stations before handling any food. And while the public rarely sees it, KFC's factory network is global but highly localized. Facilities are located close to supply chains and restaurants, so that chicken can go from bird to bucket in as little as 48 hours. Some regions operate their own prep hubs, while others rely entirely on in-store breading. Regardless of setup, the steps, the cuts, the brining, the seasoning, the breading method, the pressure fry cycle are replicated with uncanny consistency, batch after batch, store after store. So even though the end product might look simple, a crispy thigh, a golden drumstick, a perfectly breaded breast, it's the result of a highly engineered process that controls every variable, from feedlot to fryer. Every bite of KFC chicken is a small miracle of industrial food science wrapped in proprietary seasoning and delivered at a speed that only automation, logistics, and relentless procedural training can provide. McDonald's burgers may feel like fast food, but behind each patty is a global factory system built for scale, safety, and precision engineering. Millions of burgers are served every single day, and nearly all of them can be traced back to a production process that transforms whole sides of beef into standardized, flash-frozen patties in minutes. At the factory level, making a McDonald's burger isn't about cooking. It's about control of sourcing, fat content, texture, shape, temperature, and microbiological safety. It's meat processing at the scale of aerospace manufacturing. It all starts with the raw material, beef trimmings. McDonald's doesn't use mysterious filler meat or pink slime in its regular burgers. It uses 100% beef, mostly lean trimmings left over after the most valuable cuts, like steaks and roasts, are removed from the carcass. These trimmings arrive at the processing facility in large vacuum-sealed containers, chilled and tracked by batch number and origin. Every shipment is tested before it's even unloaded, scanned for temperature consistency and contamination. Inside the facility, which is refrigerated from wall to wall, the beef moves quickly from receiving to grinding, but not before it's blended. Each patty, whether for a Big Mac, a quarter pounder, or a basic hamburger, has a target fat ratio, typically around 20% fat to 80% lean. Because beef trimmings vary in fat content depending on where they come from on the cow, the factory uses a fat analysis system to create the perfect blend. Optical scanners and near-infrared sensors analyze the fat levels of incoming meat in real time. The system then pulls from different bins of lean and fatty meat and blends them together, like dialing in a recipe by percentage. This blended beef goes into massive grinders, long stainless steel augers that push the meat through ultra-sharp blades, creating a uniform texture. The meat is not overly ground. The goal is to keep the bite structure intact so the patty doesn't become mushy. From here, the ground beef flows into a forming machine, a high-pressure system that presses it into exact size patties using precision molds. Each mold is designed to create uniform diameter, thickness, and weight. For example, a quarter pounder patty is exactly 4 ounces before cooking, while a standard hamburger patty is closer to 1.6 ounces. The forming system presses the meat into a specific density to account for shrinkage on the grill, ensuring that even after cooking, it fits the bun perfectly. But here's where the engineering gets fascinating. McDonald's patties are never seasoned, never pre-cooked, and never touched by human hands once they enter the forming line. The formed patties drop directly onto a freezing conveyor belt, where they're flash frozen at 40 degrees Fahrenheit within minutes. This rapid freezing is crucial. It locks in moisture, halts microbial activity, and stabilizes the patty's shape. The faster the freeze, the smaller the ice crystals, which means better texture when cooked later. As patties move through the spiral freezer, they are spaced evenly and continuously monitored by infrared temperature sensors and metal detectors. Any patty that's not perfectly shaped, underweight, or too warm is rejected automatically and diverted for reprocessing. Frozen patties are then stacked into rows by robotic arms and inserted into cartons. These boxes are barcoded, batch-coded, and sealed, then loaded onto pallets for deep frozen storage at 20 degrees Fahrenheit, ready to be shipped to McDonald's distribution centers. Throughout this process, every movement is tracked. Each patty has a data trail that includes time of production, meat origin, grinder settings, fat ratio, freezing time, and packaging line number. Back at the restaurant level, things are equally standardized. Frozen patties arrive in boxes labeled by product type. hamburger, quarter pounder, Big Mac, and are stored in walk-in freezers. When it's time to cook, grill operators pull the exact number of frozen patties needed and place them directly onto clamshell grills. No thawing required. These grills, automated and heated on both the top and bottom, close over the patties and apply uniform pressure and heat. A standard hamburger patty cooks in about 42 seconds. A quarter pounder, which is made from fresh, never frozen beef in some markets like the US, takes slightly longer and is grilled manually in order to preserve texture. The grills are calibrated down to the degree and the cooking time is preset. There's no guesswork, only automation. As the burgers cook, excess fat and moisture drain away through grooves in the grill, while sensors monitor temperature to ensure food safety. Once finished, patties are lifted by the operator and placed into holding trays, where they're kept warm for a maximum of 10 to 15 minutes before being discarded if not served. Another strict quality control rule. No seasoning is added during production. Only salt and pepper are applied after grilling, just before the burger is assembled. This ensures the seasoning is fresh and that the meat surface stays dry enough to achieve the Maillard reaction, giving the patty a browned, flavorful crust. While the patty is the star, the buns are also factory made for exact compatibility. Hamburger buns are baked off-site in high-speed bakeries, cooled, sliced, and flash frozen to lock in moisture. They're toasted at the restaurant on dual contact toasters that heat them to 500 degrees Fahrenheit for just a few seconds, creating a warm surface that resists sogginess and clings to condiments. Each component, from the beef to the bun, is timed, measured, and assembled within seconds at the line. An average McDonald's kitchen can assemble hundreds of burgers per hour, all with patties that are nearly indistinguishable in shape, taste, and texture, because the factories that produce them are engineered to eliminate variation. Sanitation in the patty factory is non-stop. Every surface is stainless steel. Workers wear full-body protective gear, pass through air showers, and sanitize hands and boots before entering food zones. All grinders, forming machines, belts, and hoppers are cleaned in place using high-pressure foam and steam sanitation systems. Air is HEPA filtered to prevent microbial spread, and environmental swabs are taken daily for bacterial testing. No part of the system operates without data. Every piece of equipment, from the meat blenders to the freezers, feeds information into a central dashboard monitored by food engineers and safety personnel. If temperatures shift, blade pressure fluctuates, or a batch goes even slightly out of spec, alerts are sent immediately, and the line can be stopped in seconds. Even the sustainability goals are tracked here. Many factories have adopted water recycling, energy-efficient freezers, and methane recovery from meat waste. Trimmings and rejected patties are rendered and repurposed, not wasted. At full capacity, a McDonald's beef patty plant can produce over 2 million patties per day. And despite that staggering number, the quality targets are tighter than many artisanal kitchens. Each burger you unwrap may feel mass-produced, and it is, but it's made in a system where every variable is measured, every motion is repeatable, and the only acceptable outcome is a patty that cooks the same way, looks the same way, and tastes the same way, anywhere in the world. So while the end product may feel fast and disposable, the factory behind every McDonald's burger is anything but. It's a cold, stainless steel symphony of grinding, forming, freezing, and packaging. A controlled ecosystem designed to deliver something incredibly consistent at a scale few other food systems can match. Subway may be known for its made-to-order sandwiches, but the illusion of freshness at the counter is only possible because of a vast, behind-the-scenes production system. One that begins in massive factories designed to produce pre-portioned, pre-baked, and ready-to-build components for every sandwich on the menu. From the foot-long bread to the uniform stacks of meats and sliced vegetables, nearly everything is prepped in specialized food manufacturing facilities that run 24/7 to keep up with the chain's global demand. It all starts with bread, the literal backbone of every Subway sandwich. Despite being baked in-store daily, Subway's bread dough is actually produced in massive bakery plants before ever reaching a restaurant. The factories, often contracted to industrial bakers specializing in frozen dough, mix thousands of pounds of dough at a time, using high-speed spiral mixers and automated ingredient feeders that weigh flour, water, sugar, yeast, and conditioners to tight tolerances. Each type of bread, Italian, 9-grain wheat, honey oat, Parmesan oregano, hearty Italian, and more, has its own dough formula. Once mixed, the dough is divided into loaves using volumetric dough dividers that cut by weight, not by length, to ensure uniform baking later. The portions are gently rolled and shaped into long, narrow sticks on molder conveyors, then deposited onto baking trays. These trays pass through a proofing tunnel, a warm, humid chamber where yeast activates and the dough rises to its final size. But they're not baked yet. Instead, the risen loaves are par-baked, partially cooked just enough to set their structure and kill the yeast. This is done in high-capacity convection ovens running at over 400 degrees Fahrenheit. The loaves spend just a few minutes inside before being cooled with filtered air, then flash frozen on a spiral conveyor. The rapid freeze locks in moisture, preserves yeast flavor, and prevents the crust from hardening. These frozen, par-baked loaves are packed into boxes and shipped in temperature-controlled trucks to Subway locations around the world. At the store level, employees complete the baking in small convection ovens, giving the bread its warm, crusty exterior and that signature fresh-baked smell. But the structure, size, and flavor were all engineered weeks earlier in factories running like clockwork. Next up, meats and proteins. Subway's proteins are not sliced fresh in store. Instead, they're manufactured in large-scale food processing plants where uniformity is paramount. Turkey, ham, and roast beef begin as whole muscle cuts, often sourced from partner suppliers, and flash frozen upon arrival. These cuts are trimmed, brined, and then steam cooked or roasted in industrial ovens that hold hundreds of pounds of meat per batch. Brining is done under vacuum pressure to ensure full absorption of salt and flavor throughout the muscle. After cooking, the meats are chilled rapidly in glycol-cooled tunnels and sent through high-speed slicers, which slice each piece to exact thickness tolerances, usually just under 2 mm. The slices are then stacked and portioned mechanically. For instance, every serving of Black Forest ham is 4 slices, and every turkey portion is 6 slices. These are weighed automatically, with robotic hands inserting them into vacuum-sealed pouches. Each pouch contains a precise, ready-to-use portion, reducing prep time in stores and eliminating the chance of over-portioning. Subway's more processed meats, like cold cuts, salami, pepperoni, and bologna, are made through emulsification and casing processes. Raw meats are ground and mixed with spices and curing agents in vacuum blenders, then extruded into sausage casings or molded into loaves. These are cooked, chilled, and sliced with ultra-thin circular blades, moving at high speed before being packaged in airtight stacks. Then there's chicken, which comes in several forms: oven-roasted breast, grilled strips, breaded patties, and shreds for items like the rotisserie-style sandwich. Chicken breasts are tumble marinated in massive drums, where flavor and moisture are distributed through mechanical agitation. Grilled strips are cooked on conveyor belt broilers, where radiant heat and searing rollers cook both sides simultaneously before cutting into uniform strips. The cooked chicken is then chilled and packed into food service bags with oxygen absorbers to extend shelf life. Protein items, like meatballs and steak, are also made off-site. Meatballs are machine-formed, cooked in steam ovens, and flash frozen in their marinara sauce. Steak is pre-cooked, sliced, and frozen in bulk bags, often with added broth or seasoning to enhance juiciness once reheated. Nearly all of these proteins are delivered frozen or refrigerated, depending on local food safety laws and distribution times. Subway stores store them in walk-ins or lowboys, where they're portioned and prepared according to daily demand forecasts. What about vegetables? Most are pre-sliced, bagged, and shipped in cold chains from regional produce hubs. Lettuce arrives shredded. Tomatoes, cucumbers, green peppers, and onions are sliced in high-volume produce facilities using industrial slicers that sort by size, color, and ripeness. Carrots are often pre-julienned. Olives are pitted and sliced by weight, and pickles come brined and pre-cut. These produce plants clean, sanitize, and process vegetables in washed zones lined with antimicrobial flooring and ozone-treated water baths. Optical sorters remove subpar pieces before packing. The sliced vegetables are packed in modified atmosphere packaging, MAP, bags, where oxygen levels are replaced with nitrogen and CO2 to slow spoilage. Bags are labeled with time and date stamps and have a strict shelf life, often just 3-5 days. At the store, staff empty these bags into prep bins, which are rotated based on FIFO, first in, first out protocols. While tomatoes and green peppers may be sliced fresh in store in some regions, most of the work has already been done at the factory. Even cheese is precision manufactured. Subway's sliced American and provolone are pre-cut in industrial dairy plants, where large blocks of cheese are sliced using wire cutters or ultrasonic blades, then interleaved with film to prevent sticking. Shredded cheeses like mozzarella or Monterey cheddar are pre-mixed and coated with anti-caking agents before being shipped in sealed bags. Every item is packed to support Subway's global supply chain. Boxes are coded by product, lot number, and production date. QR codes link to supplier details and quality checks. Temperature sensors are built into pallets to detect cold chain failures. Everything from deli meats to banana peppers is logged, scanned, and traceable. Back in the factories, sanitation is near obsessive. All equipment is cleaned in place daily with caustic foaming agents and food-safe steam. Conveyor belts are removable and made from non-porous plastic polymers. Floors are angled for drainage and cleaned hourly. Workers wear full PPE, including gloves, hairnets, beard guards, and gowns. Entry into production zones requires passing through sanitizing air curtains and foot baths. Factory temperatures are tightly controlled. Cold rooms never rise above 41 degrees Fahrenheit. Warm zones like ovens and proofing tunnels are separated by temperature-locking vestibules to prevent microbial crossover. Air is filtered through HEPA systems to remove particulate matter and pathogens. Every food item undergoes microbiological testing, both at the production site and third-party labs. Products are sampled in real time from the line, plated onto culture media, and incubated to check for E. coli, Listeria, or Salmonella. Batches are not released until testing clears. And then there's distribution. Subway partners with a network of food service distributors who move products from regional hubs to stores every 2-3 days. Trucks are loaded using route-optimized software, and each delivery contains just enough to stock the store without overloading fridge space. Bread dough, meats, cheese, sauces, and produce all arrive together, prepped, chilled, and ready for that made-to-order illusion. In truth, the fresh assembly line at Subway is just the final 5% of a process that begins weeks earlier in factories designed for speed, safety, and consistency. Every slice of meat, every loaf of bread, every spoonful of tuna is measured, packaged, tracked, and delivered to make sure that a sandwich made in Omaha tastes exactly like one made in Orlando or Osaka. So while it may seem like your sandwich is made right in front of you, it's really the result of an entire industrial food system humming quietly in the background, mixing dough, slicing tomatoes, marinating chicken, and portioning cheese by the ton. Subway is a global sandwich brand built not just on customization, but on the relentless predictability of factory precision. And every 6-inch sub starts in a facility engineered to make fresh feel effortless. The process begins long before the chicken ever reaches the factory. KFC, like many large-scale food brands, maintains strict supply chain standards for its poultry. Birds are typically sourced from integrated poultry farms that meet the brand's animal welfare, health, and biosecurity requirements. These farms often operate under vertically integrated systems, meaning the entire life cycle of the chicken, from hatchery to grow out to processing, is managed within the same corporate ecosystem. This helps ensure uniformity in bird size, health status, and meat quality, which is critical when producing standardized menu items like spicy wings on an industrial scale. Once the chickens are ready for harvest, they are transported in temperature-controlled, sanitized trucks to centralized poultry processing plants. Here, the live birds go through a humane stunning and slaughtering process, typically involving controlled atmosphere stunning systems. This ensures both ethical handling and meat quality preservation. After slaughter, the birds are defeathered, eviscerated, washed, and cooled, typically through a cold water immersion chilling system that brings the internal temperature of the carcass down to safe levels as quickly as possible. The wings are separated during the portioning phase using high-speed automated cutting equipment. These machines use vision systems to identify and cut at precise anatomical joints, ensuring each wing is uniform in size and shape. This precision is crucial, not just for cooking consistency, but also for proper breeding adhesion and portion control in later steps. The selected wing portions, consisting of the drumette and flat sections, are then transferred to a dedicated wing processing line, where the transformation into spicy wings begins in earnest. Once the wings arrive at the spicy wing processing facility, the first stage involves a thorough inspection. Human inspectors and machine vision systems work in tandem to detect any physical abnormalities or foreign materials. Wings that pass inspection are then routed into a cold, tumbling drum, where they are lightly massaged with a saline-based pre-treatment solution. This helps the meat retain moisture throughout the cooking process and prepares the surface for better batter adhesion. At this stage, some facilities may also inject a phosphate or sodium-based marinade that helps improve juiciness and shelf life, although the exact formulation is proprietary and closely guarded by the brand. Following pre-treatment, the wings move down the line to the breading and seasoning stations, which are often the most visually engaging part of the process. First comes the wet batter application. Wings are submerged into a thin, flour-based slurry that acts as an adhesive layer for the dry coating. This slurry may contain modified starches, leavening agents, and a controlled pH buffer to ensure it sticks properly and reacts correctly during frying. After draining off excess batter, the wings are conveyed into the dry seasoning tumble. This dry breading stage is where the iconic spicy flavor is born. The seasoned flour blend used here is proprietary, but it typically includes a complex mixture of chili powders, paprika, black pepper, garlic powder, onion powder, and other flavoring agents, along with fine-grained flour and cornmeal for texture. A dusting conveyor or tumbling drum ensures even coverage on all sides of the wing. The machinery here is designed to prevent clumping and ensure that only an even, fine layer of breading adheres to each piece. In some facilities, a secondary pass through a flour press or compactor system ensures the breading is firmly embedded into the moist surface, giving it that distinctive crispy crunch once cooked. After seasoning, the wings are briefly set aside for a short dwell time. This resting phase, usually about a minute or two, allows the breading to properly adhere and partially hydrate. Next, they move into the pre-frying section of the line. This stage involves a high-capacity industrial fryer, often filled with high-stability vegetable oils, such as soybean or canola oil. The oil is heated to precisely controlled temperatures, typically around 350 degrees Fahrenheit, and the wings are flash fried for a brief period, just long enough to set the breading and create the initial crispy layer. This pre-frying step is not intended to fully cook the wings, but to lock in the structure of the coating so it maintains its texture during further processing. Once the pre-frying is complete, the wings are immediately conveyed to a blast chilling or par-fry cooling tunnel. This cooling step is critical for preserving the structural integrity of the coating and preventing carryover cooking that could degrade the texture. The temperature is rapidly reduced using forced cold air circulation, typically within a matter of minutes. Once cooled, the wings are either packaged for distribution to KFC outlets where final frying will occur, or they proceed to a fully cooked, frozen format, depending on the specific supply chain model used by the regional franchise. In systems where the wings are fully cooked at the central facility, they enter a final, high-temperature fryer that brings the internal temperature of the chicken to over 165 degrees Fahrenheit, ensuring it meets food safety standards. The duration and temperature profile of this final cook are tightly controlled and monitored by programmable logic controllers and sensor arrays that adjust heat levels in real time. The fully cooked wings then exit the fryer onto an inclined conveyor belt fitted with oil removal wipers or air knives to eliminate excess surface oil. Immediately following the cooking phase, the wings are transferred into a spiral or straight line blast freezer, depending on the plant layout. These freezers use ultra-cold air circulated at high velocity to freeze the wings down to storage temperatures of around -18 degrees Celsius. This rapid freezing process, known as individual quick freezing or IQF, prevents the formation of large ice crystals that could damage the structure of the breading and meat. The IQF process ensures that the wings retain their texture, flavor, and moisture when later reheated in KFC kitchens around the world. After freezing, the wings move into the packaging area. Here, automated systems weigh, portion, and package the wings into branded bags or cartons. Each package is checked for weight compliance using dynamic check weighers, and then sealed using high-speed heat sealers or vacuum packaging machines. Every package is labeled with traceability information, including batch codes, production time, and expiration dates, allowing for complete tracking through the supply chain. Quality control is deeply integrated into every step of this process, from metal detectors and X-ray machines that screen for physical contaminants to inline oil filtration systems that continuously purify frying oil to automated sensors that measure moisture content and temperature. Every phase of production is monitored by a combination of human oversight and real-time digital systems. Facilities that produce KFC spicy wings typically operate under globally recognized food safety standards such as HACCP and may also be certified under schemes like BRCGS or SQF. Once the wings are packaged, they enter the cold storage logistics chain. Pallets of frozen wings are loaded into refrigerated trucks that maintain a strict temperature range throughout transportation. These trucks deliver the product to regional distribution centers and eventually to individual KFC restaurants. In some regions, fresh, never frozen versions of the wings are delivered in chilled format and cooked to order in-store. In other areas, particularly where supply chains are longer or temperatures more variable, the IQF model is used to ensure quality is preserved until the point of sale. At the restaurant level, the final stage of the journey unfolds. Frozen or chilled wings are stored in temperature-controlled environments until needed. When ordered, the wings are deep fried one last time in high-capacity fryers, typically operating at around 350 degrees Fahrenheit. This final fry crisps the coating, rehydrates the spices, and brings the product to serving temperature. The result is a spicy, crispy, juicy wing that delivers the iconic KFC experience customers have come to expect. The process begins with the raw foundation of the product, the humble potato, but not just any potato will do. The ideal potato for Taco Bell nacho fries is typically a variety high in dry matter content, often russet Burbank or Shepherdy types, known for their low moisture, high starch, and robust structure. These characteristics ensure the fries achieve the perfect balance between a fluffy interior and crispy exterior after frying. These potatoes are sourced from large, vertically integrated farms primarily located in the Pacific Northwest of the United States or similar potato-producing regions around the world, where the climate and soil are optimal for consistent, large-scale yields. Harvesting is done using advanced mechanical harvesters that dig up the potatoes and gently lift them onto conveyor systems to avoid bruising. From there, they are transported to centralized washing and grading facilities where they are sorted by size, inspected for blemishes or defects, and washed thoroughly using high-pressure water jets and rotating brushes. Any potatoes that do not meet the factory standards are diverted to other uses such as dehydrated flakes or animal feed. Once approved, the potatoes are delivered in bulk to industrial fry manufacturing plants where the transformation into nacho fries begins. At this stage, they are held in temperature and humidity-controlled storage rooms to preserve their starch content and prevent premature sprouting. When it's time to process, the potatoes are first sent through a series of peelers, usually steam peelers or abrasive roller systems, that efficiently remove the skins while minimizing product loss. This step is closely monitored using yield tracking sensors to ensure peeling efficiency and minimize waste. The peeled potatoes are then sliced using high-speed industrial cutting machines fitted with grid blades that create uniform fry shapes, typically thicker than traditional fast food fries to support the added seasoning and prevent oversaturation. These slicing systems are calibrated down to the millimeter to ensure each fry is cut to precise specifications, generally around 1 4-inch to 3 8-inch thickness. High-pressure water flumes carry the sliced fries through the line at speeds exceeding 20 feet per second, ensuring rapid, continuous processing. Next comes the blanching stage, where the sliced fries are briefly immersed in hot water, typically around 170 to 180 degrees Fahrenheit, for a few minutes. This partial cooking phase serves multiple purposes. It removes excess surface sugars that could cause uneven browning during frying, activates enzymes that improve texture, and begins the gelatinization of internal starches. After blanching, the fries are quickly cooled using chilled water or air blast tunnels to stop the cooking process and firm up the structure. Now partially cooked, the fries enter the par frying line. This is their first encounter with oil, and it's where the initial crispy layer begins to form. Large industrial fryers filled with high stability oil, such as a blend of sunflower and canola oils, are heated to around 350 degrees Fahrenheit. The fries are submerged for a precise amount of time, usually less than 90 seconds, just long enough to form a protective crust on the outside. Sensors and computerized fry time controllers ensure that oil temperature remains consistent to prevent flavor degradation or uneven cooking. Immediately after par frying, the fries pass through a de-oiling conveyor, where vibrating belts and air knives remove excess surface oil. The fries are then conveyed into a seasoning chamber, which is one of the most distinctive stages in the production process. Here, Taco Bell's proprietary spice blend is applied. The exact recipe is tightly controlled, but it's known to include ingredients like paprika, garlic powder, onion powder, chili powder, and finely milled salt, combined with natural flavor enhancers and color stabilizers. A continuous tumbling drum with angled paddles ensures every fry is evenly coated, while fine misting sprays may be used to lightly dampen the fries and help the powder adhere without making the product soggy. Once seasoned, the fries are flash frozen using a high-velocity IQF freezer system. In this stage, powerful cold air, chilled to minus 40 degrees Fahrenheit or below, is blasted across the fries in a spiral or linear tunnel. This rapid freezing process locks in flavor, moisture, and structure, preventing ice crystals from damaging the surface coating. The IQF method ensures that each fry remains separate and doesn't clump, which is critical for later portioning in restaurant operations. After freezing, the fries are transferred to the packaging line. Automated systems weigh and fill bulk fry containers or food service size bags, which are then sealed using heat sealing equipment. Each bag is printed with a batch code, production date, and temperature tracking markers. Metal detectors and X-ray machines scan each package to ensure no foreign materials are present, a key component of food safety compliance. Packaged fries are loaded onto pallets and stored in deep freeze warehouses until they are ready for distribution. The nacho cheese sauce, an essential companion to the fries, has its own equally rigorous production process. The base of the sauce is typically a processed cheese blend made from cheddar, milk proteins, and emulsifying salts like sodium citrate or sodium phosphate. These ingredients are carefully combined in industrial kettles equipped with steam-jacketed heating systems and high-shear mixing paddles. Stabilizers, such as modified starches and gums, may be added to ensure the sauce maintains a smooth, pourable texture even after cooling and reheating. Once the cheese base is prepared, spices are added, typically a blend of jalapeno flavoring, chili extract, and other proprietary ingredients that give the nacho sauce its signature kick. The mixture is emulsified under vacuum to remove air bubbles and then pasteurized using a continuous flow heat exchanger. This process heats the sauce to over 165 degrees Fahrenheit for a controlled amount of time to destroy microbial contaminants while preserving flavor and color. After pasteurization, the cheese sauce is hot-filled into sterilized pouches or cups under aseptic conditions. These containers are then sealed and either cooled through a water cascade system or sent into spiral chillers. The sealed containers are packed into cartons and labeled for refrigerated or shelf-stable distribution, depending on the formulation used for the region's supply chain. With both the fries and the cheese sauce packaged and preserved, the products are transported through a cold chain logistics network. Fries are shipped frozen in insulated trucks to regional distribution centers and then delivered to Taco Bell restaurants in freezer-safe cartons. The cheese sauce, often refrigerated, follows a separate cold storage route. Each location has specific temperature monitoring systems in place to ensure food safety compliance throughout transit and storage. At the restaurant level, the frozen fries are stored in walk-in freezers until needed. When an order comes in, the fries are portioned out and deep fried in vegetable oil, using high-efficiency commercial fryers. This final fry is where the crispy golden texture is fully developed. The temperature is maintained at a consistent 350 degrees Fahrenheit, and the fry time is usually between 2 and 3 minutes. Once cooked, the fries are immediately drained, then served hot in Taco Bell branded packaging. The cheese sauce is reheated either in a hot holding unit or using a hot water bath system that brings it to serving temperature without burning. The sauce must reach at least 140 degrees Fahrenheit to meet food safety and quality requirements. Once heated, the sauce is portioned into small dipping containers or drizzled directly over the fries in some menu variants. Throughout the entire industrial journey of nacho fries, rigorous quality assurance and food safety protocols are in place. Samples from each batch are taken at various stages and tested for microbiological contaminants, seasoning distribution, oil content, moisture levels, and cooking performance. Facilities operate under strict guidelines such as FDA, FSMA requirements or international standards like ISO 22000 and HACCP. Every element of production, from the slicing of potatoes to the pasteurization of cheese sauce, is documented and auditable to ensure full traceability. The process begins with the heart of the Whopper, the beef patty. Burger King has long differentiated its burgers by using a flame-grilled method, but before the grill comes into play, the patty must first be produced. Beef is sourced from large-scale, certified suppliers that adhere to strict animal welfare, traceability, and sustainability standards. These suppliers operate integrated meat processing facilities where cattle are harvested and broken down into primal and subprimal cuts under USDA or equivalent oversight. The beef used for Whoppers is typically derived from a mix of chuck, round, and sirloin cuts, blended to achieve a desired fat content, often around 20%, for optimal juiciness and grill performance. Once the meat is ground, it is passed through an emulsifying system that ensures even distribution of fat and protein. This step helps prevent gristle pockets and improves the patty's binding structure. The ground beef mixture is then conveyed to high-speed patty-forming machines that press and extrude the meat into uniform rounds using a die plate and compression mold. These industrial formers operate at speeds of hundreds of patties per minute and are capable of adjusting thickness and diameter to exact specifications, typically around a quarter-pound raw weight for each Whopper patty. The formed patties are placed on a conveyor belt and flash frozen using cryogenic tunnel freezers or spiral IQF systems that use liquid nitrogen or carbon dioxide to rapidly bring the internal temperature below -18 degrees Celsius. This ensures that each patty retains its cellular structure and juiciness upon cooking. Once frozen, the patties are transferred to automated packaging lines, where they are stacked in moisture barrier cartons or vacuum-sealed pouches, labeled with production dates, and passed through metal detectors before being palletized for frozen storage and global distribution. Equally important to the Whopper is the bun, a sesame seed-topped, split bread roll that undergoes its own industrial journey. Buns are produced at high-capacity commercial bakeries where production lines can generate tens of thousands of units per hour. The dough is made from a blend of wheat flour, water, sugar, yeast, and vegetable oil, along with dough conditioners and preservatives to maintain softness and shelf life. The mixing phase involves large-scale planetary or spiral mixers that knead the dough to the correct gluten development. After mixing, the dough enters a resting phase in fermentation-proofing chambers where it rises under controlled temperature and humidity. The dough is then portioned by volumetric dividers and shaped into balls by automated rounders. These pre-shaped dough pieces are loaded onto proofing trays and undergo a final rise before baking. The tops are lightly misted with water or egg wash and sprinkled with white sesame seeds by mechanical applicators. The buns are baked in continuous tunnel ovens that stretch over 100 feet in length and operate at temperatures exceeding 400 degrees Fahrenheit. Once baked, they pass through a rapid cooling system using ambient or chilled forced air to bring their temperature down before slicing. Each bun is sliced horizontally by high-speed rotary blades and inspected for consistency. To maintain freshness, buns are either packaged in modified atmosphere packaging or frozen shortly after cooling and then bagged in polyethylene liners. They are coated with traceability information and packed into corrugated cartons for delivery to regional warehouses and restaurants. The vegetables, lettuce, tomatoes, and onions are sourced from contracted agricultural operations that follow strict GAP protocols. Iceberg lettuce, preferred for its crunch, is harvested using semi-automated field machines that cut and core the heads in one motion. The lettuce is then transported in refrigerated trucks to processing facilities where it is washed in sanitized flumes, dried using centrifugal systems, and shredded using stainless steel cutting blades designed to preserve crispness without bruising the leaves. Tomatoes are selected for firmness and uniform diameter to ensure neat slices. They are cleaned using high-pressure spray washers and sliced using rotary slicers fitted with adjustable blades. The sliced tomatoes are layered into stackable trays or nested compartments to prevent crushing during transit. Similarly, onions are peeled mechanically using high-pressure air systems, sliced into rings, and packaged under chilled conditions to retain freshness. The pickles, another key flavor component, are made from cucumbers processed in bulk brining tanks. After harvest, cucumbers are washed, sorted by size, and submerged in a vinegar-based brine seasoned with salt and spices. After fermentation or quick pickling, depending on the formulation, they are sliced into consistent chips using high-speed slicers and packaged in oxygen barrier pouches or buckets for food service use. Condiments for the Whopper, primarily mayonnaise and ketchup, are manufactured in specialized condiment production facilities. Mayonnaise production begins with the emulsification of oil, egg yolk, vinegar, and stabilizers in high-shear mixing tanks equipped with homogenizers. The emulsion is pasteurized through a plate heat exchanger to eliminate pathogens while preserving viscosity and color. Ketchup is cooked in steam-jacketed kettles and blended with tomato concentrate, sugar, vinegar, and a proprietary spice mix. Both condiments are filled into sterile plastic pouches, bag-in-box systems, or pump-compatible canisters for use in restaurant dispensers. Cheese slices used in variants like the Whopper with cheese are produced from processed cheese blends that ensure meltability and consistency. These are extruded into sheets, cut into slices, and layered with separators to prevent sticking. The slices are then vacuum packed or nitrogen flushed for refrigerated storage and distribution. With all components produced and shipped to Burger King locations, the final assembly of the Whopper occurs in the restaurant, but the process is built upon a strict operational framework. Each location stores the beef patties in a walk-in freezer and thaws them under refrigerated conditions. When an order is placed, the patty is cooked on Burger King's signature broiler, a chain-driven flame grill system that uses open gas flames to charbroil the beef as it passes through on a conveyor. This broiler, unique to Burger King, is a marvel of fast food engineering. The system allows for consistent flame contact, resulting in seared grill marks and a characteristic smoky flavor. Sensors monitor patty temperature and broiler speed to ensure the patty is fully cooked to a safe internal temperature of 160 degrees Fahrenheit without overcooking. The cooked patties are briefly held in warming trays under precise time constraints to maintain texture and temperature. Meanwhile, the buns are toasted in a dedicated bun toaster, which uses radiant heat or infrared technology to give the interior a light crispness while leaving the exterior soft. The assembly station is laid out for ergonomic speed and accuracy. A Whopper bun base is placed on a wrapping sheet or clamshell box. The bottom bun receives a layer of mayonnaise, followed by shredded lettuce, 2 to 3 tomato slices, and the flame-grilled patty. Next come the ketchup, sliced onions, pickle chips, and finally the top bun. Employees are trained to follow a specific build order and ingredient placement protocol to maintain consistency across all locations. Once assembled, the Whopper is either wrapped or boxed using pre-printed branded materials and placed into warming cabinets for immediate delivery to the customer or drive-through window. Food safety, quality assurance, and traceability are enforced at every step of the Whopper's life cycle. Raw materials are tracked via digital systems that log harvest dates, batch codes, and production facilities. Burger King suppliers and franchises are subject to regular third-party audits, temperature verification, and microbiological sampling. Any deviation from standard operating procedures, whether it be in patty cook temperature, bun freshness, or condiment integrity, triggers corrective action protocols. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses: never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling, rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 G. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In-store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction. Chef Boyardee beef ravioli begins its industrial journey with the delivery and preparation of raw ingredients in a tightly controlled, high-capacity food processing environment designed for continuous, large-scale output. At the very start, Durum wheat semolina arrives in bulk and is stored in tall silos connected by enclosed pneumatic systems that transport measured amounts of flour into industrial mixing vats. These mixers operate under vacuum to prevent air entrapment in the dough, which could compromise the texture of the final pasta. Water is injected through a flow-regulated system, and the dough is mixed into a dense, elastic mass that is then conveyed into a dough sheeter. Inside this machine, large stainless steel rollers gradually press the dough into a long, uniform sheet of precise thickness. Sensors constantly monitor and adjust roller pressure, sheet thickness, and alignment in real time, ensuring consistent dimensional control across thousands of linear feet of pasta every hour. As the pasta sheet continues on its route, it approaches the forming station. Here, the sheet is split into top and bottom layers using a synchronized cutting system, and the beef filling, prepared simultaneously on a parallel line, is introduced between them. The beef mixture is produced in massive steam-jacketed kettles, where ground beef is cooked with tomato paste, spices, salt, and stabilizers. High-shear mixing blades ensure uniform blending, while thermal sensors regulate the internal temperature to avoid overcooking. Once cooked, the beef filling is transferred to positive displacement pumps that feed the filling directly into the ravioli former. Precise nozzles inject a consistent amount of filling at evenly spaced intervals onto the bottom sheet. The top sheet is laid over it, and the two layers are pressed together by a rotary die that seals and cuts the individual ravioli pockets in one continuous motion. Any excess dough around the edges is collected and recycled back into the dough feeder. The freshly formed ravioli travel along a mesh belt through a par cooking tunnel, where a curtain of low-pressure steam partially cooks the pasta just enough to firm the structure and set the seal. The par cooking chamber is followed by a high-efficiency air chiller that quickly cools the product to prevent further cooking. From here, the ravioli move to the accumulation table that feeds the canning line. The tomato sauce, which is made in a separate set of kettles, is already being prepared in parallel. This sauce includes tomato puree, vegetable oil, spices, and sugar, blended in high-capacity vats, equipped with wall-scraping agitators to ensure uniform cooking and prevent scorching. The sauce is filtered to remove any large solids, skins, or seeds, and is kept hot in jacketed holding tanks while waiting to be dispensed. The canning line is a seamless, high-speed process that brings ravioli and sauce together inside sterilized metal cans. Empty cans are first fed from depalletizers into an inverted position for steam or air sterilization before being returned upright and carried along a conveyor. A timed filling system first drops a preset quantity of ravioli into each can. Next, a separate nozzle dispenses a specific volume of hot tomato sauce into the same can. Load cells and vision sensors measure weight and volume in real time, instantly rejecting any can that falls outside tolerance. To maintain long shelf life, the filled cans receive a quick injection of steam into the headspace to displace oxygen, which is critical for preventing spoilage and discoloration. The cans then proceed to the seaming machine, which applies and crimps the metal lids at high speed using rotary chucks that spin and press the lids into place with a hermetic seal. Once sealed, the cans are routed into a massive rotary retort, a large pressure chamber where the canned ravioli undergo commercial sterilization. This thermal processing step is one of the most critical phases in the entire operation. Inside the retort, the cans are exposed to pressurized steam at temperatures above 121 degrees Celsius for a fixed period, calculated according to product density, can size, and altitude. The process is tightly controlled by a programmable logic controller that adjusts heat input, steam pressure, and timing with precision, ensuring that the interior of each can reaches the temperature needed to destroy any potential microbial contaminants. This sterilization method allows the product to be shelf stable for over a year without the use of chemical preservatives. As the cans exit the retort, they are rapidly cooled using a countercurrent water system that brings the internal temperature down quickly while avoiding thermal shock that could warp the can. After cooling, the cans are dried using air knives that blow off any surface moisture. They then move into the labeling area where each one is printed with a unique production code, expiration date, and batch number using high-speed inkjet printers. These codes are logged in a centralized database that allows full traceability of every can, linking it back to the exact batch of dough, filling, sauce, and sterilization cycle. This traceability system is essential for maintaining quality control and complying with food safety regulations. Labels are applied using rotary labelers, which align the cans, dispense the adhesive-backed labels, and press them smoothly onto the curved surfaces. Any can with a misapplied or missing label is automatically diverted off the line. The labeled cans proceed to the packing station, where they are grouped into shrink-wrapped multi-packs or loaded into cardboard trays, depending on distribution requirements. Robotic arms equipped with vacuum suction heads stack these cases onto pallets in a tightly packed, interlocked pattern that ensures transport stability. Each pallet is weighed, stretch-wrapped, and labeled with a scannable barcode that encodes the full logistics data for shipping and warehouse integration. Completed pallets are conveyed into a climate-controlled warehouse area, where ambient temperature is maintained within a narrow range to preserve product integrity and packaging quality. The inventory system automatically logs each pallet into a virtual grid based on product type, batch, and destination. Orders from distribution centers are matched against inventory using software that assigns retrieval instructions to automated guided vehicles. These vehicles transport the pallets to loading bays where they are prepared for shipment on temperature-managed trucks. Throughout this entire process, every step is monitored by industrial control systems that log thousands of data points per minute, from moisture content in dough to the pressure in the retort chamber. If any sensor detects an anomaly, whether it's a filling inconsistency, temperature deviation, or mechanical irregularity, alarms are triggered, and corrective protocols are initiated automatically. Quality assurance technicians also perform random sampling at every stage, testing dough elasticity, filling viscosity, source pH, seam width, and internal vacuum levels. Any sample that fails a parameter prompts an investigation and potential quarantine of the related batch. The design of this factory setup allows for continuous production for 24 hours a day, with modular maintenance schedules that let individual lines shut down without halting the entire operation. Cleaning-in-place systems run through every tank, pipe, and pump at regular intervals, using cycles of hot, caustic solution, followed by acid rinses and pure water flushes. This level of automated sanitation prevents bacterial buildup and maintains a sterile environment, especially critical in the post-cook zones. By the time a single can of Chef Boyardee beef ravioli reaches the supermarket shelf, it has passed through dozens of machines and control checks, undergone multiple thermal transformations, and been assembled from raw materials that were processed, cooked, combined, sealed, and sterilized within minutes of each other. The result is a uniform, shelf-stable product that replicates the exact same taste, texture, and aroma across millions of cans each year, a feat of engineering, timing, and integrated automation performed at industrial scale. The industrial production of gnocchi begins with a continuous intake of raw potatoes selected specifically for their starch content, moisture levels, and uniformity. These potatoes arrive in bulk, often delivered in heavy-duty totes or truckloads, and are immediately transferred into stainless steel receiving bins. From here, a water flume system propels the potatoes toward the washing stage using a circulating stream of filtered water. which not only moves the product gently, but also performs a preliminary rinse that separates dirt, rocks, and field debris. The potatoes pass into a rotary drum washer, a large cylindrical cage lined with soft baffles and rotating paddles. Inside, multiple high-pressure spray jets clean the surface of every tuber, while slow drum rotation ensures even exposure. Wastewater is filtered and recycled back into the flume, maintaining efficiency while minimizing fresh water consumption. Once cleaned, the potatoes move onto inclined conveyor belts and pass beneath an optical sorter that detects misshapen or heavily blemished specimens. Air jets eject any defective potatoes instantly. The remaining load proceeds toward the steam peeling chamber, a sealed environment into which high-pressure steam is injected rapidly. This process loosens the skins in seconds without penetrating deeply into the flesh. A sudden pressure drop follows, causing the skins to rupture. As the chamber releases its load, rubber fingers or gentle high-pressure sprayers remove the loosened skin without damaging the underlying structure. The peeled potatoes then travel along a belt for final inspection before cooking. Next, they enter a cooking tunnel equipped with rotary steam ovens or belt-fed boiling sections. These systems are calibrated to cook each potato evenly, using internal probes to track core temperature without overcooking the starch. The cooking time is precisely tuned so the flesh softens just enough for mashing while preserving structural integrity. Cooked potatoes are discharged directly into screw-fed conveyors that deliver them into industrial mashing systems. These mashers force the hot potatoes through perforated plates using rotating paddles, breaking them into a uniform, lump-free mash with consistent density. This mash is transferred into stainless steel hoppers, fitted with agitators to prevent settling while it awaits mixing. Simultaneously, dry ingredients are prepared using a separate set of feeders. Wheat flour, salt, and any dry seasonings are metered in precise ratios using volumetric or gravimetric dispensers, ensuring repeatable consistency across large batches. These dry components meet the hot mash in horizontal ribbon mixers or twin screw extruders, where the dough is developed. If eggs or other binders are used, these are injected through nozzles timed to match the flow rate of the dry and wet components. Dough temperature, torque, and consistency are continuously monitored, allowing automated systems to adjust mixing speed or ingredient dosing in real time. As the dough reaches its final form, it exits into forming lines. These lines are fitted with multi-head extrusion units that shape the dough into cylindrical ropes, which are automatically guided into a cutting module. Guillotine blades or rotary knives slice the ropes into uniform pillow shapes at high speed. Each piece is then transferred onto a vibrating sorting table to prevent clumping and ensure even spacing before shaping. For traditional gnocchi, a patterned drum or stamp roller presses the surface of each dumpling, forming the signature ridges. These ridges aren't just for appearance. They help hold sauces and ensure the texture is consistent during cooking. The raw gnocchi are now ready for par cooking. Depending on the product type, they may enter a steam tunnel, boiling water bath, or continuous blanching system. For fresh gnocchi, a short steam treatment helps gelatinize the starch on the outer layer, setting the shape without fully cooking the interior. In the case of shelf-stable or refrigerated products, boiling is used for more complete cooking. The gnocchi travel through the system on mesh conveyors that allow water to drain or steam to vent. Those that float prematurely, often indicating trapped air or structural failure, are skimmed off and diverted. Finished gnocchi are cooled rapidly with air or chilled water sprays to stop the cooking process immediately. Cooling is followed by drying. Par-cooked gnocchi are passed through air tunnels or oscillating belts with forced, filtered airflow. This surface drying stage ensures the pieces don't stick together in packaging. In some configurations, a fine coating of semolina or rice flour is applied to further reduce surface tackiness. At this stage, the gnocchi are fully formed, partially cooked, and ready for packaging or freezing depending on the final product category. Fresh gnocchi are directed into multi-head weighing systems that portion exact quantities into pre-formed pouches. These machines calculate the best weight combination from multiple hoppers to ensure precision. Pouches enter a modified atmosphere packaging (MAP) chamber, where the ambient air is replaced with a mix of inert gases like nitrogen and carbon dioxide. This extends shelf life by inhibiting microbial growth and oxidative reactions. Sealing jaws then close each pouch under pressure, forming airtight seals. Pouches exit the MAP system and are immediately inkjet printed with production codes, expiration dates, and batch tracking information. For frozen gnocchi, the cooled pieces bypass MAP and instead travel to the freezing tunnel. This is a long conveyor system housed within an insulated chamber where fans blow extremely cold air across the product. The process is known as IQF, or individual quick freezing, which ensures that each gnocco freezes separately, avoiding clumps. Once frozen solid, the gnocchi are packaged in bulk or consumer-ready bags, sealed, labeled, and sent to deep freeze storage. Regardless of the format, every package goes through a metal detection and X-ray inspection station before final packing. These machines identify any potential contamination from production, like stray metal fragments from worn machine parts, and immediately reject any affected units. Packages that pass inspection proceed to robotic case packers, where arms equipped with vacuum grippers load them into cardboard boxes. The boxes are sealed, barcoded, and sent to automated palletizers that stack them according to optimized loading patterns. Each pallet is stretch wrapped and labeled with a traceable QR code or barcode, then entered into the warehouse management system. The final stage is cold storage and distribution. Refrigerated products are stored at 2 to 5 degrees Celsius, while frozen products are kept at 18 or colder. High-density shelving is managed by ASRS units, automated storage and retrieval systems that navigate the warehouse floor with programmed efficiency. When an order is placed, the system retrieves the correct pallet, stages it at the loading dock, and synchronizes it with outbound transport logistics. Goods are typically moved in temperature-controlled trucks that maintain strict thermal stability to prevent texture loss or microbial growth during transit. Quality assurance labs operate in parallel with the production floor. Technicians pull random samples from each batch to assess moisture content, cooking time, bite texture, and microbiological safety. These samples are cooked and evaluated for structure, flavor retention, and resistance to disintegration. Texture analyzers apply calibrated pressure to measure chew resistance, while high-resolution cameras measure shape retention after boiling. If a batch fails any parameter, the corresponding lot is flagged in the system and held for further review or disposal. Cleaning and maintenance operations take place in modular shifts. All lines are fitted with cleaning in place (CIP) circuits, automated wash systems that flush tanks, hoses, pumps, and valves with caustic solutions, hot water, and acid rinses. This ensures hygienic conditions even when production is running continuously. Key areas like mashing stations, flour feeders, and packing heads receive manual cleaning daily, and critical equipment like extrusion heads are dismantled, brushed, sanitized, and reassembled before every major production run. Throughout the process, every detail is monitored by supervisory control and data acquisition (SCADA) systems. These systems provide operators with real-time dashboards showing dough temperature, flow rates, extrusion torque, cutter speed, par cooking dwell times, and fill weights. Alerts and automated corrections ensure that even minute deviations are caught and resolved without interrupting production. Historical data is stored and reviewed to improve yield, reduce waste, and maintain traceability. From field harvested potato to the final sealed pouch or frozen bag, gnocchi production at factory scale is a precisely tuned sequence of heat, pressure, shaping, and preservation, all balanced to protect the soft, pillowy character that defines this classic product. What begins as humble starch and flour becomes thousands of identical dumplings per hour, delivered with perfect form, flavor, and shelf stability. Lasagna production in a factory is a multi-phase, highly integrated process that combines pasta sheet manufacturing, meat sauce preparation, cheese blending, layer assembly, baking or pasteurization, portioning, packaging, and cold chain logistics, all synchronized to ensure consistency, safety, and scale. Unlike dry pasta or single-element products, lasagna is a fully prepared, multi-ingredient dish. This makes its industrial production uniquely complex, requiring extensive machinery and tightly controlled automation to ensure that every slice mirrors the expected texture, flavor, and structure. The process begins with pasta sheet production. Durum semolina flour is delivered in bulk and stored in silos. From there, it moves through pneumatic conveyors into high-capacity mixing vats where it's combined with water under vacuum. This vacuum mixing reduces air bubbles and improves dough elasticity. The dough is then extruded into wide sheets using continuous sheeting rollers. These rollers compress and stretch the dough between pairs of calibrated rollers, gradually flattening it to a specific thickness, typically less than 1 millimeter. Optical thickness sensors positioned along the rollers feed data into a closed-loop control system that makes micro-adjustments in real time. The continuous pasta sheet is then guided onto a conveyor that passes through a high-temperature dryer tunnel. This dryer uses forced hot air to reduce surface moisture and firm the sheet slightly without fully cooking it, which gives it the pliability needed for layering. After drying, the sheet moves into a cutting system. Depending on the product specifications, a rotary knife assembly cuts the sheet into wide rectangular panels, each aligned with the intended tray dimensions. A rejection arm automatically discards any sheets that are torn, folded, or non-uniform. While pasta sheets are being prepared, the factory simultaneously produces the meat sauce. Ground beef is loaded into steam-jacketed kettles equipped with high-speed agitators. The meat is seared first, breaking it into small crumbles. Tomato puree, tomato paste, oil, chopped onions, garlic, herbs, and seasoning are metered into the kettles through automated valves. The sauce is simmered while being agitated to prevent scorching and ensure uniformity. During this time, inline temperature probes and brick sensors monitor thickness, sugar levels, and viscosity. Once the sauce reaches its target consistency, it's pumped through heated stainless steel pipelines into holding tanks that maintain it at a constant temperature until assembly. In a separate mixing area, the cheese component is prepared. Depending on the recipe, this may include a blend of ricotta, mozzarella, and parmesan. Ricotta is delivered in cooled totes and mixed with stabilizers, herbs, and sometimes eggs in vertical mixers to ensure even distribution. Shredded mozzarella and grated parmesan are stored in silo-like hoppers connected to vibratory feeders that portion out cheese by weight for each layer. Now begins the core of the lasagna production, layer assembly. This takes place on a continuous assembly line with moving trays or belt-mounted mold forms. Each tray or mold is sanitized prior to filling and travels under a set of ingredient dispensers. First, a measured amount of meat sauce is deposited into the bottom of the tray by a servo-controlled nozzle that moves in a sweeping pattern to ensure full coverage. A vacuum depanner then places a single pasta sheet on top, aligning it precisely over the sauce. This is followed by a ricotta deposit nozzle that pipes a uniform, ridged bead of cheese across the sheet, which is then smoothed by a vibrating spreader bar. Another pasta sheet is placed, and the cycle repeats, sauce, pasta, cheese, until the required number of layers is achieved. The top layer typically ends with sauce and a sprinkling of shredded mozzarella and parmesan dispensed by oscillating auger heads that shake cheese evenly over the tray surface. Before baking or pasteurization, some lines include a brief compression station where a flat paddle gently presses down on the lasagna to remove air pockets and improve bonding between layers. The fully assembled trays then move on to the thermal treatment phase. If the lasagna is intended to be frozen, the thermal step may be pasteurization, which involves heating the product just enough to kill bacteria but not fully cook it. For chilled or ready-to-eat versions, full baking is performed. Trays enter a convection oven that circulates heated air at over 180 degrees Celsius. The line speed, tray height, and internal oven temperature are all controlled to ensure even cooking from edge to center. Internal temperature probes inserted in sample trays verify that core temperature targets are achieved and held for a specific time to guarantee food safety. Once cooked or pasteurized, the lasagna must be cooled rapidly to prevent microbial growth and lock in texture. This is done through a tunnel chiller, where trays pass through zones of progressively colder air, sometimes supplemented by glycol-cooled plates that pull heat from the tray bottoms. The cooling process must reduce the product from over 80 degrees Celsius to below 5 degrees Celsius within a few hours, which is regulated by airflow, dwell time, and temperature differential. Sensors at the tunnel exit confirm that each tray meets cooling requirements. Once cooled, the lasagna is portioned and packaged. If individual servings are required, the tray is sliced by ultrasonic knives that vibrate at high frequency, cutting cleanly through dense layers without dragging or distortion. For family-size portions, the entire tray may be sealed as is. Packaging formats include vacuum-sealed trays, film-sealed thermoformed, packages, or sealed and labeled foil trays, depending on the target market. Modified atmosphere packaging may also be used for chilled products to extend shelf life. Oxygen levels are flushed and replaced with inert gases before the final seal is applied. Each sealed package passes through a metal detector and X-ray unit to ensure it contains no foreign materials. It then receives an inkjet printed label showing the batch number, production date, expiration date, and a scannable code for traceability. The labels are verified by vision systems to confirm placement, readability, and correctness. Any mislabeled unit is automatically rejected into a separate channel. From there, packages are grouped into boxes using robotic case packers. These cases are palletized by automated arms that stack them in stable formations, alternating layers for weight distribution. Stretch wrapping units seal the full pallet, and each is tagged with a warehouse tracking code before being moved to cold storage. Depending on the product type, it may be stored in refrigerated or frozen conditions. Pallets are managed by automated guided vehicles that transport them to pre-assigned racks in high-density storage systems, where inventory software tracks position, age, and destination. Throughout this process, the factory uses a SCADA, supervisory control, and data acquisition system to monitor every critical variable. Dough hydration levels, pasta sheet thickness, sauce viscosity, cooking times, and packaging seal integrity are all tracked in real time. Historical data is stored and analyzed to identify patterns, correct deviations, and optimize throughput. If any parameter falls outside the designated range, alarms are triggered, and the system automatically isolates affected batches for inspection. Cleaning and sanitization cycles are embedded throughout the plant. Clean-in-place systems run through the pasta extruders, sauce kettles, and piping lines at scheduled intervals. Belts, mixers, and conveyors are cleaned using automated foamers and high-pressure rinsers between production runs, often overnight. This ensures the plant can shift from producing meat lasagna to vegetarian or gluten-free variants without cross-contamination. Every few hours, quality assurance teams perform manual inspections of randomly selected trays, assessing factors such as layer adhesion, ingredient distribution, flavor profile, pH level, and slice integrity. Cooking tests are conducted to see how the product behaves in a domestic oven or microwave, ensuring the consumer experience matches factory standards. The entire process, from flour and raw meat to finished boxed lasagna, is designed for speed, consistency, and hygiene. Trays of lasagna move continuously through a loop of automation, blending traditional culinary elements with industrial engineering. The meat must be savory but not greasy. The pasta should remain tender after reheating without breaking apart. The cheese should melt and set without seeping or becoming rubbery. Each of these qualities is maintained not through guesswork but through precise mechanical control over every movement, temperature change, and ingredient ratio. Spaghetti production in factories begins with the precise blending of durum wheat, semolina, and water in massive stainless steel mixers that rotate at controlled speeds to ensure uniform hydration. The semolina used is specially milled to have a coarse texture that provides the ideal structure for pasta, unlike finer flours used in bread or cakes. Water is added in exact ratios, typically around 30 to 33% by weight, to activate the gluten without making the dough too sticky or too dry. The mixing process takes approximately 15 to 20 minutes, during which sensors monitor temperature and moisture levels to prevent overheating or uneven consistency. Once the dough reaches the right consistency, it is fed into a vacuum deaerator that removes trapped air bubbles, preventing imperfections during extrusion. This vacuum step is critical because air pockets can cause the spaghetti to break or cook unevenly later in the process. The dough then enters a twin screw extruder, where hydraulic pressure forces it through bronze or Teflon dies with hundreds of tiny holes arranged in precise circular patterns. Bronze dies are preferred for traditional pasta because they create a slightly rough surface that holds sauce better, even though they wear down faster than Teflon. Each die is engineered to produce strands exactly 2 millimeters in diameter, with tolerances of less than 0.05 millimeters to maintain consistency across entire production runs. As the dough is extruded, it emerges as continuous strands that are immediately cut into standardized lengths of 25 to 30 centimeters using high-speed rotating blades. The cut strands are gently guided onto moving conveyor belts made of food-grade polymer that prevent sticking while allowing airflow underneath. These belts carry the spaghetti into the first drying chamber, where temperature is held at 35 degrees Celsius, and humidity is kept below 60% to begin slow moisture removal. Drying is not a single-step process. It occurs over 4 to 6 hours across multiple zones, with gradually decreasing humidity and increasing temperature. In the initial drying zone, moisture is slowly drawn from the outer surface of the strands to prevent cracking or surface hardening. The second zone raises the temperature to 45 degrees Celsius while reducing relative humidity to 40%, allowing moisture to migrate from the core outward. In the third zone, the temperature climbs to 55 degrees Celsius and humidity drops to 30%, accelerating the drying of the pasta's interior without collapsing its structure. A final conditioning zone at 30 degrees Celsius and 55% humidity allows the pasta to equilibrate, ensuring even moisture distribution throughout each strand. Throughout the entire drying process, robotic arms with infrared sensors continuously scan each batch for cracks, warping, or discoloration, automatically diverting defective strands. After drying, the spaghetti is cooled in a controlled environment to room temperature over the course of 90 minutes to prevent condensation and microbial growth. Cooling is done with filtered, dehumidified air to avoid reintroducing moisture that could lead to spoilage during packaging. Once cooled, the strands are gently shaken and separated by vibrating screens that disentangle any strands that may have adhered during drying. A powerful airstream then blows away any residual semolina dust or small fragments that could affect texture or shelf life. The spaghetti is then fed into precision weighing systems that portion out exact quantities, typically 500 grams or 1 pound, into food-grade polypropylene bags. Each bag is sealed with heat, creating an airtight barrier that protects against oxygen, moisture, and pests for up to 2 years. Inside the sealed bag, a small oxygen absorber packet is often included to further extend shelf life by eliminating residual oxygen. Before sealing, a metal detector scans each package to ensure no foreign materials, such as metal fragments from machinery, have contaminated the product. The packaged spaghetti is then labeled with batch numbers, expiration dates, and nutritional information using high-resolution inkjet printers that operate at speeds exceeding 100 packages per minute. Each label is scanned and logged into a centralized digital tracking system that links every box to its exact production time, raw material source, and quality control checkpoints. The boxes are stacked by robotic arms onto pallets, wrapped in stretch film, and moved via automated guided vehicles to a climate-controlled warehouse. The warehouse maintains a constant temperature of 18 degrees Celsius and humidity below 50% to preserve the pasta's texture and prevent mold. Before shipment, random samples are pulled from each batch and sent to an on-site laboratory for microbiological testing, including checks for salmonella, E. coli, and mold spores. The lab also performs texture analysis using a texture analyzer that measures the firmness of cooked spaghetti to ensure it meets the industry-standard al dente criteria. Each batch is tested for cooking time, with the target being 8 to 10 minutes in boiling water, and deviations trigger an automatic review of the drying parameters. Once cleared, pallets are loaded onto refrigerated trucks that maintain a steady 10 to 15 degrees Celsius during transit to prevent thermal degradation. The entire production line operates 24 hours a day, 7 days a week, with only brief scheduled maintenance windows to clean and inspect critical components. Every hour, the extruder dies are manually inspected and cleaned with high-pressure steam to prevent bacterial buildup in the microscopic holes. The mixing tanks are sanitized with food-grade citric acid solutions after every batch to eliminate cross-contamination risks between different pasta shapes. Workers in the facility wear full hairnets, gloves, and shoe covers, and all entry points have air showers that blow away dust and particles before entry. The factory's HVAC system filters air 15 times per hour, maintaining a Class 8 clean room environment to meet international food safety standards. All equipment is designed with smooth, seamless surfaces and no crevices where dough or debris could accumulate and become a breeding ground for microbes. Robotic vision systems monitor the color and shape of every strand exiting the extruder, rejecting any that deviate from the established visual profile. If a strand is found to be too thick, too thin, or irregularly shaped, the system automatically adjusts the extrusion pressure in real time to correct the issue. The factory produces over 12 million kilograms of spaghetti annually, enough to feed approximately 200 million servings per year. Each kilogram of finished spaghetti requires precisely 1.1 kilograms of semolina, with the remaining 0.1 kilogram lost to moisture evaporation during drying. The water used in production is filtered through reverse osmosis systems to remove minerals that could affect dough texture or flavor. Wastewater from cleaning is treated in an on-site biological filtration plant before being safely discharged into municipal systems. Used semolina dust is collected and sold to livestock feed manufacturers, reducing waste and contributing to a circular economy model. The energy used in drying is partially recovered through heat exchangers that capture exhaust heat and reuse it to preheat incoming air. The factory's lighting system uses motion-activated LED panels that dim or turn off in unoccupied zones to reduce electricity consumption. Every machine on the line is connected to a central AI monitoring system that predicts maintenance needs based on vibration patterns and motor load. This predictive maintenance reduces unplanned downtime by over 40% compared to traditional scheduled servicing. The factory's quality control team includes food scientists with PhDs who regularly test new semolina varieties and drying algorithms to improve efficiency, New production runs are always preceded by a trial batch that undergoes sensory evaluation by trained tasters who assess texture, aroma, and mouthfeel. Each factory worker undergoes quarterly food safety certification and participates in simulated contamination drills to maintain readiness. The entire process, from raw semolina to sealed box, takes less than 7 hours from start to finish, making it one of the most efficient food manufacturing systems in the world. No preservatives are added to the spaghetti, relying entirely on low moisture content and airtight packaging for long-term stability. The final product contains no cholesterol, no saturated fat, and no added sugar, making it a nutritionally neutral staple in global diets. Every strand of spaghetti produced in this facility is identical in diameter, length, density, and cooking behavior to the one before it, thanks to relentless automation and real-time feedback systems. The factory operates with zero tolerance for human error in the final packaging stage, as even a single mislabeled box could trigger a nationwide recall. Lasagna production in factories starts with a dense, coarse semolina flour blended with chilled, purified water in a slow-turning horizontal mixer that prevents overdevelopment of gluten. Unlike spaghetti dough, lasagna dough is formulated to be slightly drier and more rigid, enabling it to hold its shape during stacking and baking without becoming soggy. The water used is pre-cooled to 12 degrees Celsius to maintain dough temperature below 24 degrees during mixing, preserving the natural starch gelatinization profile. After blending, the dough is rested for 15 minutes in a sealed, humidity-controlled chamber to allow gluten strands to relax and absorb moisture evenly. This resting phase is critical. It reduces the risk of sheet cracking during the subsequent rolling process by allowing internal tension to dissipate. The dough is then fed into a tandem roller system composed of hardened steel cylinders that compress the dough in 7 incremental passes, each reducing thickness by only 0.08 millimeters. The final roller gap is set to 0.62 millimeters, producing sheets so uniform that laser sensors can detect deviations as small as 0.01 millimeters across the entire width. As the sheets emerge, they are immediately swept by a gentle stream of dry, filtered air to prevent adhesion to the metal conveyors and to initiate surface drying. The sheets are not cut immediately. Instead, they travel continuously along a 30-meter long drying track suspended above a series of radiant infrared heaters. These heaters emit targeted wavelengths that dry the top and bottom surfaces at different rates, minimizing curling and warping caused by uneven moisture loss. Humidity sensors embedded in the drying tunnel adjust airflow in real time, maintaining a gradient that pulls moisture from the core outward without forming a hard outer shell. Every 12 seconds, a robotic arm lifts a section of the continuous sheet and tests its tensile strength by gently stretching it between calibrated claws. If the sheet fractures or elongates beyond 12% of its original length, the system flags the batch and adjusts the next dough batch's hydration level automatically. Once dried to a moisture content of under 10%, the sheets are cooled in a tunnel filled with recirculated, sterile air to prevent reabsorption of ambient moisture. At this stage, the lasagna sheets are still flexible enough to be handled without breaking, but too brittle to be rolled back into dough. A high-speed cutting station then slices the continuous ribbon into individual rectangles using tungsten carbide blades that operate at 1,200 cuts per minute with zero blade wear. Each piece is precisely 10.2 centimeters wide and 15.5 centimeters long, sized to fit standard commercial lasagna pans and retail packaging dimensions. After cutting, the pieces are lifted by electrostatic air knives that use controlled static charges to separate and align them without physical contact. They are then conveyed over a vibrating platform that gently shakes off residual semolina dust, which is collected and recycled into animal feed. The sheets pass through an ultraviolet sterilization chamber that eliminates surface microbes without altering taste, texture, or nutritional value. Each sheet is individually inspected by a machine vision system that scans for color consistency, surface texture, and the presence of any embedded foreign particles. Defective pieces are ejected into a waste bin using compressed air jets, while acceptable sheets continue to the packaging line. Packaging occurs in a sterile environment where each lasagna sheet is placed into a pre-formed, food-grade cellulose tray lined with a moisture barrier film. The trays are sealed under vacuum with a heat seal lid that creates an airtight barrier, extending shelf life to 18 months without preservatives. Inside each sealed tray, a small silica gel packet is inserted to absorb any residual moisture that might develop during transit or storage. Before sealing, each tray is passed through an X-ray scanner that detects metallic contaminants, plastic fragments, or glass particles invisible to the naked eye. Every package is labeled with a unique QR code linked to its production batch, ingredient source, and quality assurance logs accessible via manufacturer portals. The sealed trays are stacked by robotic arms onto pallets wrapped in heat shrink film, then moved by autonomous guided vehicles to climate-controlled storage. Storage rooms maintain a constant 16 degrees Celsius and 45% relative humidity to prevent brittleness or microbial growth over extended periods. Random samples are pulled daily and sent to the in-house lab for cooking tests, where technicians measure rehydration time, firmness after boiling, and sauce absorption rate. The target is for each sheet to absorb exactly 45 milliliters of water in 8 minutes of boiling, achieving a texture that remains firm yet pliable under cheese and sauce. Lasagna sheets are never pre-cooked. Their dry state is intentional, allowing consumers to layer them directly into casseroles without blanching. The entire production line runs continuously, processing over 800,000 sheets per hour, with each machine synchronized to within 0.01 seconds of the next. Maintenance is performed during scheduled 15-minute windows every 4 hours, during which steam jets clean every surface the dough contacts. No lubricants are used on any part of the machinery that touches the dough. Instead, food-grade silicone coatings are applied to rollers to prevent sticking. All personnel entering the production area must pass through an airlock chamber that blows away particulates before entry, and gloves are changed every 30 minutes. The factory's ventilation system filters air 22 times per hour, maintaining a particulate count lower than that of a hospital operating room. Every batch of semolina is tested for protein content before use, with only flour yielding 12.5 to 13.2% gluten accepted for lasagna production. The water used is reverse osmosis, purified and mineral balanced to ensure consistent dough behavior across different regional water sources. Wastewater from cleaning is treated with activated carbon and UV sterilization before being reused for non-food contact purposes like floor washing. Unused semolina dust is sold to organic fertilizer producers, and packaging film scraps are recycled into industrial plastic pellets. Energy recovery systems capture heat from the drying tunnels and redirect it to pre-warm incoming water, reducing overall energy consumption by 37%. AI algorithms analyze vibration patterns in the rollers and predict bearing failures up to 72 hours in advance, eliminating unscheduled downtime. Each lasagna sheet is designed to expand by no more than 3% when cooked, ensuring layers remain flat and evenly distributed in the finished dish. No additives, preservatives, or enzymes are used. Only semolina, water, and time. The final product contains zero cholesterol, no trans fats, and less than 0.1% sodium, making it suitable for dietary restrictions worldwide. Each sheet is identical in weight, thickness, and cooking behavior to every other sheet produced in the last 10,000 batches. The factory produces enough lasagna sheets annually to assemble over 50 million individual lasagna dishes, each one ready to be layered, baked, and served. Once packaged, the trays are loaded onto refrigerated trailers that maintain a steady 8 to 12 degrees Celsius during transit across continents.